Good morning, ladies and gentlemen. Very nice to see you all here. I'm glad about everyone who has joined us online as well. Today, we have very special people here who are very different, but all of you are some kind interested in environmental pollution and in how to end it. My name is Elina Kolate. I'll be the moderator of the discussion today. Tomorrow, you will go to see in practice, in real life, how the remediation of Karosta Channel looks like. But today, we'll stay indoors, thanks God, and talk about researches and job that you all have been doing. Let me introduce you to our first speaker, CEO of Liepājā Special Economic Zone, for the opening of the party. Yes, please tell us what's so special about Liepājā Special Economic Zone.
Hello, very happy to see you here in Liepājā, in our city. To this conference. This is a very important event because we are, as you know, doing a very important project for cleaning up Karosta Channel, and so environment is one of our top priorities here in Liepājā. But I think you will have a lot of discussions and conversations about environment. I will my introduction speech tell a bit different then maybe will be other topics during today. So a little bit about Liepājā, a little bit about Special Economic Zone. Yeah. So Liepājā is, we are in this beautiful building, concert hall, Great Amber. Liepājā is a modern city that combines global outlook with the comfort of a small town. This is slogans that we use quite often, and this actually shows because it's not big city, but it's with rich cultural traditions, with port, with manufacturing, and a lot of other things, and it's all combined in very compact place. We have set a target that by 2030 Liepājā is going to be climate neutral city and smart city. Computer is very slow today. So by 2027, Liepājā is also going to be a European cultural capital. Yeah, so this is great achievement that we have contested, and so this is going to bring in Liepājā a lot of cultural events. And Liepājā, what it is, so it's quality of life. It combines business environment, it combines educational establishments, family-friendly sports, outdoor activities, arts and culture. So those who have been here, I think you have all tried. But it has not always been like that. Yeah? So I will show some pictures of how it looked actually 30 and 40 years ago. In the 50s, when Latvia was part of Soviet Union, it was special law was set that Liepājā will be transferred, Liepājā port will be transferred to Navy. So this is just a few pictures. You see how munition is loaded to submarines. This is how it happened in Liepājā port in Karosta Channel. I think one of such a failed loading we found during excavation works of Karosta Channel this year. So it was quite big bomb. And such a views submarines were quite common in Liepājā port. So this is area, if you can see, so it's loads of Navy ships in areas where currently we are loading grain, servicing ferry to Germany, etc., etc. So all port was absolutely Navy and closed to the people who lived here, to Liepājā people. So, but how it was left when Navy, Soviet Army left Liepājā, it started to look like that. A lot of sunken ships, a lot of pollution, a lot of oil into the water, into the ground, fences that were made from batteries filled with acid, and that all was going into the ground. So you can imagine amount of pollution that we had. And actually port was absolutely devastated maybe is the right word. We had to do something to turn port from Navy port to commercial port. And that's why in 1997, 7 years after we got independence, law about special economic zone was established with the aim develop port, manufacturing, trade, industrial territories, airport, and perspective development territories. So this included 2/3 of Liepāja city area, including port, including manufacturing territories, airport, and others. And this is just a few pictures how it looks today. Everything that is done here is actually built in last 20, 30 years. New terminals, loading grain. This is a picture from Karosta, from Navy channel. So it's also being transferred from Navy channel to commercial channel, and grain and other cargoes are being transshipped to other countries. So we started in 1991 with 0, and last year we set new record for Liepāja port, 7.6 million tons. So, and we hope that next year's will be even more. If you want to travel to Germany, so it's 6 times a week greenest way how to get to Germany, because we know that water transport actually gives the smallest amount of emissions per ton of cargo transported. So you can easily get to Travemünde, and from Travemünde actually to any other destination in Europe with a good railway system. We are also a new destination for cruise ships. And something interesting, currently is being built drinking water export terminal. So this is something new. If other countries has oil or other gold, black gold, so we have transparent gold. Liepāja has permit to use 10 million cubic meters of water per year, but we are currently using approximately 3.5. Yeah, so we have approximately 6 million tons of water that we can still get out of the ground. And so local business people came up with the idea with the partners that this is possibility for Latvia to export our resource, and this is water, to the countries where this is required, like Africa, and where there is deficit of water. And so terminals being built, gonna be completed beginning of next year, and hopefully actually planning that next year first ships will start to deliver water to countries where it is needed. And also Liepāja International Airport with major reconstruction can service Air Baltic flights and charter flights, and you can get access to Liepāja. And we are thinking about new projects like offshore wind. This is gonna be built in Latvian waters and wind parks and other locations near Liepāja. And we believe that Liepāja port is best location where to establish base for offshore wind farm construction. And so we are working on it. And this is visualization how it should look. Approximately 40 hectares of new territory in Liepāja port, where both assembling of wind farms can happen, both some new manufacturing, like manufacturing of towers, etc. And of course, that is why we are here all today. Very huge for us project, Karosta Canal cleanup that we are completing this year. Liepāja is not only port city, Liepāja is industrial city with long heritage. Picture something like 120 years ago. So it's 19th century. Liepāja grew very fast from 10,000 people in beginning of century till 100,000 people in the end of the century. A lot of factories were built, a lot of accommodation was built, and people came as to development city. But of course, manufacturing those days looked like this with black smoke chimneys. And this is not 100 years old picture. This is just 15 years ago when Liepāja Steelworks was still functioning. So this was everyday view when I was going to, as a children was going to school. We looked, Steelworks was working like that. But of course, it was biggest manufacturer, biggest employer, biggest taxpayer, not only in Liepāja, but in Latvia in general, biggest exporter, biggest consumer of electricity and gas, etc., etc., etc. So, and yeah, and this is one video, yeah, how actually factory worked, and yes, I think no comments here. We have hot spots, still quite many in Liepājā city that we still have to clean up. This was a way how in Soviet times it was normal way to run manufacturing. It's water. It's water that actually is near the lake. It's not connected to lake, this particular channel, but it's 10 meters from Liepājā lake, that is Nature 2000 lake. Yeah, but so manufacturing also was stopped in 90s because it was oriented to Soviet Union markets, so no demand for products that were produced in Liepājā was demanded anymore. And territories were also abandoned. And so we started to work on development of industrial territories, development of manufacturing. This is Karosta, Navy part of city, also was polluted and abandoned, and we turned it into a nice industrial park by building streets, making places for new factories, cleaning it all up. And so it looks absolutely different as it looked 30 years ago. Old meat factory, working in Soviet times, sending products to St. Petersburg, abandoned in 90s. One Danish guy came, bought it, and turned it into, I would say, successful business park where many companies have started and built, actually expanded. Yeah. So now it's 4 times larger than it was in Soviet times. And some 6 years ago, we started to draw this map because after collapse of steelworks, unemployment was very high, and people, actually everybody said, what is the biggest problem in Liepājā? So it's jobs, jobs, jobs. Yeah? And so we set a plan that within 4 years' time, we have to build 10 factories in Liepājā. Actually not build ourselves by special economic zone or by city, but actually convince private investors that Liepājā is the right place where to do this, where to build those factories. And so we have, from 2017, when we started to draw this map, so we have exceeded our target. 20 factories have been built, and some more are being built, and some more still under design phase. So it's actually, it's very easy to put those pins on the map, but it was not that easy when we started to this. Industries, metalworking, textile, electronics, construction, shipbuilding and repair. So that's basically biggest players. And it is graph. So year 2012 that steelworks was still working. So 2013 it stopped. So you see very huge collapse. And 2022 we already reached €500 million turnover here in Liepājā manufacturing output, and we hope that in next few years we will exceed amount of turnover that was when steelworks was still working, but we are doing it in different way, with no smoke in the air, with no pollution, in a clean, modern way. And this is our next biggest project, transformation of metallurgical plant. We are planning to turn it into new, green, modern industrial park where new companies can come in, and more than 3,000 new jobs can be created. But we have to do a very huge job. We have to clean it. We have oil pond. We have some radiation as well. So we have a lot of challenges to get done here. Yeah, but so the main thing, I think, this last slide, you know that Liepājā is a city where the wind is born. Yeah, so we have welcomed you with how we usually welcome. Yeah, either it with sun is shining and we can go to the beach, either it's windy as it is today. This is picture just a couple of days ago when all Latvia was suffering from trees who were falling. So what we did, we went to the beach and enjoyed it when wind is blowing. So thank you, and enjoy your day in Liepājā and tomorrow, and enjoy the conference. Thank you very much.
Thank you. It was Uldis Chmiļevskis, CEO of Liepājā Special Economic Zone. I have to admit that your presentation was great, because yesterday with our guest from Finland, we were actually talking about the questions like how many people live in Liepājā? You covered it. Is it the third or the fourth biggest city in Latvia? You covered it. Are there any passenger ferries in Liepājā port? You covered it. And how big is Liepājā port in general? You covered it. And wind energy, is it a thing in Liepājā? You covered it. So you are actually talking about the things people are interested in. That's fantastic. Today, that's what we are going to do. We are talk about things we are all interested in. But before we start, some house rules. House rules for the audience. Those who are watching us online, please feel free to ask your questions. If you don't feel comfortable with asking in English, ask in Latvian, I'll translate them. The same actually applies for you here. If you want to ask a question and you don't feel comfortable with English, that's fine. Ask in Latvian will help to translate it. However, when to ask questions? It will go like that. First presentation, second presentation, third presentation, fourth presentation, and then we have a time for discussion. All speakers will come here, and then we can ask all our questions. We'll have a discussion, but we all know that the real discussion starts in a coffee break. So after that discussion, we'll have the real discussion in a coffee break. Rules for the speakers. You all have 20 minutes. You know that. I have a 5-year-old son, and when he does things I don't want him to do, I tell him, I am counting to 3. 1, 2, and I never get to 3 because he stops, works like magic. I have no idea what will I do when I reach 3. I have never thought about it. It has never happened. So I'll do the same. When you have 3 minutes left, I'll show this. When you have 1 minute left, I show this. What happens after? I don't know. Anyway, when the audience feels like asking a question, please raise your hand. I'll give you the microphone. Of course, we hear each other here very well, but those for us following online, they will not hear your comments or questions if we don't use the microphone. And as we will be here for a pretty long time, we'll spend here whole day. Obviously, it is hard to sit for such a long time. If you feel like standing up, going around, going to toilet, please feel free. That's allowed. That's it. No more rules. Everything else is up to you, and I really hope we'll have fruitful discussions, and I hope that we will learn a lot. First of our speakers, Saija Sārni. She's from University of Turku. Saija, yes, please come here. And Saija will tell us more about controls and consequences of material transport within the land sea continuum. Please, floor is yours.
And I guess I can figure out how this works. Yes. So, good morning, everybody, and thank you for the invitation. It's nice to be here in a windy Liepājā, but I will take you right away to another corner of the Baltic Sea. So, I am a geologist and mostly working on sediments and trying to understand processes that control sedimentation in all kinds of environments, from lake systems to estuarine systems. And my research area that I'm going to talk today is archipelago sea, that is kind of an exception within an exception. You all know Baltic Sea quite well, and it is already quite particular place on the earth because of its rather shallow depth and brackish water. And archipelago sea is located in the southwestern corner of Finland, and what is particular to that area, it is really shallow. So when somebody from Sweden, southern Sweden, watches the Baltic Sea, he or she thinks it's the mean depth is approximately 600 meters. But when somebody from Turku thinks of what is Baltic Sea, you get an impression on the sea area that with the mean depth of 23 meters. And I think this is not very far from what you experience in Riga Bay with the mean depth of 26 meters or so. But what is different from Riga Bay in this particular area is the islands. We have more than 40,000 islands, and it has a result that we have really complex bathymetry. So this is a transect of our research area, and it's 45 kilometers long, and you see there is a lot of semi-detached basins with deeps and sills, and the sea surface is not, it's far from flat at this area. What is also special in this part is the isostatic uplift. So because of the former ice sheet, that the northern part of the Earth was kind of pushed down, and now the crust is recovering from that, and the land rises approximately 5 millimeters per year in that particular area, and it is expected that within 2,000 years from now we can just walk to Sweden. I'm not sure how many Swedish people there is. Are we waiting for that, or do we want to keep our cruise ships to shuttle between Stockholm and Turku? But there is nothing we can do for that. But the complex bathymetry caused also a lot of trouble to us. So, like the entire Baltic Sea area, it suffers the extensive eutrophication. And while we can see some hope, for example, in the Gulf of Finland, the water quality has improved after we started to manage our nutrient flow to sea system. But in Archipelago Sea, we don't see any improvement. And it is partly because of the bathymetry and because of the semi-detached areas. We don't get really that much oxygen in the bottom. They turn to anoxic, and that is called dead zones. Nothing lives there when there is no oxygen, and that induces internal loading. So at the Archipelago Sea, the internal loading is even a bigger problem than the external flooding, but we don't know how to manage it because it's a natural system. What arises from anoxic sediments, and that is something, of course, for a geologist, we like it because we can have these annually laminated lake sediments that are also called varves. And here in the picture you can see the laminated structures. So they are like tree rings, and we can just count backwards in time these couplets. And because of these varved sediments, we can calculate when the bottom became anoxic. So in my study area, we already see that all the eutrophication started much before 1950s, but it turned to anoxic already 110 years ago. And we have similar results all around the Archipelago Sea. So we've been dealing our human businesses for a long time period. Don't get shocked by this image. It is from Ambio by Vahtera and others. But I like to show it because everything is there. This is the problem that we have. So when we have external input of phosphorus, we get increased planktic and algae flumes that creates more of organic material. So when the algae, they fix fix phosphorus from the water column, and the cyanobacteria fix nitrogen from the air. And when they die, they sink through the water column on the bottom. And on the bottom, when this biogenic material decays, it consumes oxygen. And because of the thermal stratification on the summertime, the oxygen from the topmost water is not really moving to the bottom, and we just run out of oxygen. And what then happens is that in anoxic environment, the buried phosphorus that we have put there in the sediments is dissolved and released back to the water column. And that induces more phosphorus on the surface when the water is mixed on the fall. And now we have the machine up and running, and we don't really know how to stop it. And for certainly it's gonna take ages to stop these internal loads. So what we are doing now is using sediment traps to study in detail the seasonal sediment fluxes and what controls the organic matter transport from catchment to the system, and also nutrient transport to the system, and how weather or future climate change is going to change this system. Our transect is around the Kemia Island in the coastal Finland, and it is estuary with 2 branches, and the length of the branches is approximately 45 kilometers in total for both of them. What is great in sediment traps, the technology is really, really easy. Basically, you just put 2 tubes on the bottom, mooring just like 1 meter on top of the seafloor, and it collects everything that is about to settle to the seafloor. Sediment trap looks quite dirty when it comes back from the ocean, and sometimes there has been an entire fish decaying in the tube, and well, it is too much for me, but we have brave soldiers in our lab to dissolve the fish away and then work with at least the minerogenic part. We use boats. This is our research vessel, Aurelia, that we use, but the system is very small, so you can do it from a small boat as well. First results from the sediment traps you can see instantly when you get it back from the sea. So, of course, you can use your eyes and also your nose, because the oxic, like healthy, fresh sediment does not really smell, but anoxic sediments, they do smell like quite sulfur, like a rotten egg-ish. So if you catch a fluke before the field trip, it is just fine. But you can see from the trap, from the anoxic basin, it is really clean. It's like we put it there just yesterday, even if it's been there for 6 months. And when there is oxygen, there is always biofouling occurring on the surface. So the tube that looks quite furry, it is covered by a kind of polyp, and it is from the river mouth where the water is. It has a lot of clay particles and sand particles in the water column, so Secchi depth is like 10 centimeters or so. So there is no light for algae, but there is oxygen for polyp who don't need light. Just sometimes, so only one time actually, we really hit the interface where the water column turned from oxic to anoxic, so you can really see where the biofouling starts when there is enough oxygen, and when it's not enough, it is just not enough. I have some results for a monitoring period of 2 years, and what is particular for these 2 years is that I don't know, I'm not sure if you can really see what is green and what is blue from there, but the green one is summer 2018, and the blue in the below describes the winter period. And what is particular in the upper part of the picture you can see the snow cover. So first winter was really traditional winter in a sense of increasing snow or snow piles and good 30 centimeter of ice on top of the estuary, and the next winter never came. So it was just a 6-month misery, like a never-ending November with recurrent storms and a lot of rain and snow, and not snow, but and wind. And the next figure maybe you can focus on the green columns. They are calculated sum of water level changes within 1 month, and because water level, we don't really have water level changes outside from the weather connections. So when we get the low pressure, moving low pressure cells, they, like what we experience here today, they cause precipitation, but they also induce water level changes in that channel that are particularly important in terms of the sedimentation. The first summer was slightly warmer than the second summer, and the second summer was slightly rainier and cooler than the first summer. So how does the sediment then look like? We have studied everything that we can think of from the sediments, but I will guide you through this figure. But first we could just look at the winter data. So the winter of 2019 was really like a traditional winter, and from the satellite image you can see the ice cover that lasted for nearly 3 months, which is quite particular and nowadays. And compared to next winter, from the satellite image you can see there is no ice. The only white thing in the image is cloud, and you can see it's even quite difficult to recognize which part is land and which part of the picture is actually the sea area. There is so much material coming from the catchment to the water. And we can see it in our sediment accumulation rates, SAR, that is left. So you can see that it is nearly 4 times more sediments accumulating during the stormy open sea winter conditions compared to normal sea. And what comes with it, we also measured phosphor, like record phosphor release at the archipelago sea at the same year. And it increases the flux of total organic material. I don't have a pointer, but maybe I can just show. Organic flux is this one, and also the amount of terrigenous organic material accumulating, but also total amount of organic planktic material accumulating. And this is a bit of problem because all the biogenic material, when it decays, it eats and consumes the oxygen, so it is actually like giving more fuel for oxygen burning and more fuel for spreading dead zones. And when the dead zones spread, we also have increased dissolving of phosphorus from the sediments. So in that terms, the climate change, or how to protect this part of Baltic Sea, is only or also through the fighting against the climate change. What can we see from the total organic? So there is 2 components: the total flux of how much of organic material is coming from how many grams per square meter per day, but there is also organic material percentile, and the concentration of organic material in the winter sediment of 2019 is higher because there is no available mineralogic material from the land. When the land is covered by snow and ground frost, nothing moves there. So during the next winter, when there was no ground frost or no ice, everything, when it was raining, everything from the surface ground was washed to the sea. And that is, I think, because the summer values are more or less the same. So what is most important of the stages of the archipelago sea area is the winter conditions that can make a larger influence on that area. So then we can look at the summer. So this was the warmer summer, and the next one was the cooler summer with the more precipitation. And again, we can see more sediment inwash related to the precipitation. And yes, what we also get from the second winter is increased phosphor loading, which of course relates to the cyanobacterial blooms that we know from the entire Baltic Sea area. So there are multiple spatial controls for the accumulation, and here you can just see the sediment accumulation rate, how it varies. In the river mouth, the most controlling factor for the material that is sedimentating is the conservative accumulation based on the density driven. So basically large and heavy particles are when the current speed decreases, they are accumulated on the river mouth. And then the other thing that has a strong influence is resuspension caused by these storm activities. So especially the areas that you can see here and here are experiencing a strong resuspension because the trap number 9, it is surrounded by large shallow areas that are easily exposed for the storms. And trap number 10, it is like a narrow funnel, so the flow speed increases and that removes more material, and that's why we have big sedimentation there. We've done some modeling for the flow velocities, and you can see that there is a bit, I have 2 ways of calling the trap. So there, trap number 11 shows that more red, the more currents you get. So basically, this figure explains what we see in trap number 10 or 11 in the picture. Also, flocculations controls the organic material transport, and it is caused by the terrigenous dissolved organic material that enters to sea and faces the saline water. They produce flakes, and the flocculation shown, is the mid-estuarine side, and that we can see in our, for example, trace metal concentrations. So much of the trace metals are related to the organic matter. They are catched by the flocculation, and the high concentrations are occurring in the mid-estuarine. And while some particles move with the mineralogic material, and they decrease along the gradient. So the climate change and the internal phosphor loading is the largest problem in the archipelago sea. And I think it is also because things change so slow. So it is also a question of communication. So how do we communicate and say that, yes, we are doing right things, but things won't change very fast? Thank you.
You're exactly on time.
Perfect.
Thank you, Saya. You can take a seat. And the questions, I bet, will follow in the discussion. Now it's a turn for Toms Ceļmillers from the State Environmental Service of Republic of Latvia. Toms will talk about digital transformation of the contaminated site management. The floor is yours.
Thank you. Yes, my name is Toms, and I am a system analyst of a project of digital transformation of the contaminated site management. I'm sure many of you were expecting to see my colleague Madara Zinger, which you know well, who is a professional of contaminated site management. My area is more of a digital issues of the project, but if I cannot answer your specific questions on contamination management, I will gladly have your email, and we can respond and prepare answers together with my colleagues. Yes, the contamination itself, it's not digital at all. It is physical. It is the management of it is complicated, and it's very expensive. And here in these pictures you can see one of the most polluted sites in Latvia, that was Inčukalna Gudrona Dīķi, which was lakes filled with gudrons, which is a side project of cosmetics manufacturing. And also this project is one of the projects that, together with other large-scale projects, as you will probably learn about Karoste, that was successfully remediated. So here you can see the process, and here you can see the result, and you can visit this site and see that now it looks like a golf course after a successful remediation. But if we have data about what kind of pollution we have in Latvia, that mostly it's oil, and it's old like oil refineries or gas stations or other objects where like heating centrals where oil was used. And also this is the main contamination type together with other types. And what kind of data we have now about contaminated sites? Here is, we have a register that has about 3,600 sites. Most of them are potentially contaminated. That means that they might as well not be contaminated, but then we need to have the research and documents that prove it. This data is also a bit limited now, as it is. It has some coordinates, and coordinates are the only geospatial information on these sites. And maybe some have a bit more information, like about the contaminated area. So that's why we also have a lot of issues with this existing and the previous model as it was, and the reason we have our project is, that first of all this data that I showed about 3,000 sites, it was collected mostly during one project on 2003-2004. So it means that this data is 20 years old. Most of it is not really updated, and you can also question the quality of the data because, at the project maybe there were also included a lot of potentially contaminated sites by the knowledge of that time, and then maybe actually as we see the contamination now, it could be that they are not contaminated at all. The process that we have now is based on the document exchange in a paper or electronic form. So we just review a lot of documents, and we that very valuable data that can be analyzed and used stays in this form that cannot be used by analytics or other data-driven solutions. And the information, of course, if it's like in this form, then it's not circulating very well also between the state institutions, because to use geospatial data, the coordinates, it's a very limited, just one point in the map, but much better is that if you have an area that you can put on a map, then it can be also transferred and more efficiently managed in the systems that calculate, for example, the value of the property, the cadastre, because now the contaminated site restrictions apply to the whole cadastre. So it means that you cannot do any activity, building or economic activity, if you have on your whole property. And yeah, and also we have a lot of good and interesting data in archives that may help with the reorganization and improvement of the data quality that we have. So that's why we have our project, the transformation of contaminated site management model, and the first what we started with is to draw a process. This is not meant from reading, this is just an illustration, so this is the way the things are now, and this is our model that we have created on which we base future development. One of the activities of our project is digitization of archive materials. There's a very interesting archive in our project partners have in Latvian Environment, Geology and Meteorology Center. Actually, this archive can be accessed by anyone. It's like a library. We just only have to arrange the meeting. So, of course, we try to connect these digitized materials to the contaminated sites or in our registry. Yes, and the transformation, the digital transformation really starts with the creation of information systems. So basically the register data is turned to used as a base to new information systems. So in the system we have data data is standardized and structured. So it can be used and reused and electronically available for other institutions and for the society. Then we can use the data, of course, the information can be exchanged to the other state registries. And the whole process of dealing with the contamination can be done in a digital way in our system. The geospatial data of, as I told you, now we have the coordinates, but with the implementation of the system, we will have about new sites, we'll have all the information, more detailed information, starting with the sampling points, data of laboratory analysis of these points, and the most important is this based on this data we can make a contaminated site area model. So by this improvement, the data is no longer that can be used to calculate the value of the cadastre based only on that contaminated area, and you can use for economic activity all the other part of your property. And yes, the map tools, of course, they are also very helpful to plan the remediation process, because as you add layers and you see more and more data, you can better assess and arrange the remediation based on visualized layered data on a map. And of course that our approach has been in the first to think about our client, which is basically the owner of polluted sites. The actors that are from the society side also are licensed merchants, which are doing the research, remediation, and monitoring. And the owners can use the data in the system. Actually, this list of the merchants that are in the system is already in our database, so you don't need to search for it. You just see, okay, there's a merchant who has a license, and I can authorize it to start the processes of research or remediation. And of course, as an owner, you can also follow the information which is happening about what is happening to your site, follow the reports and communication of your merchant with the state environmental service. Yes, for the merchants, it is a new tool to give information, to give it in structured form, and to add data. Maybe also professionals nowadays use information systems and create geospatial data, which you can import to the system already. So you don't have to do these drawings or the paper documents with the drawings and printouts. And all the reports that needed can also be submitted to the system. And what is doing our institution in this process? We are, first of all, like the most important work probably that everyone's interested is the change of the category of the site. That is to change it to non-contaminated category, what we would like. And yes, we do it based on the documents and data on the system. And we also have a lot of processes which can be done easier with the system, where we can arrange the supervision of the research, remediation, and monitoring. So basically, these are the key elements of our project. And let us know if you have any other questions. Thank you.
Thank you so much. You can take your seat, and the questions will follow in the discussion part. Please keep in mind your questions, and also those who are watching us on Facebook pages of Baltijas krasti, Baltic Coast, or Liepājā Special Economic Zone, Liepājā Speciālā ekonomiskā zona, or YouTube channel of Liepājā Special Economic Zone. Please write down your questions. English, Latvian, doesn't matter. We'll ask them anyway. The third speaker is Linda Fībiga from Latvian Environment Geology and Meteorology Center about the significance of polluted areas in river basin management. The floor is yours.
Yes, thank you. Yes, I'm Linda Fībiga from Latvian Environment Geology and Meteorology Center. I represent the part of the environmental departments in our organization. As well, I represent project Life Good Water Integrated Project, which is very, very connected to these water management issues. And later on, there will be only one slide about our big project also. If we are talking about ecological if we are talking about river basin management, planning and all the processes, I usually show this map, which represents the water ecological quality in Latvia. So what does it mean, ecological water quality? It means that we take into account three big parts of environmental parameters. One big part is physical-chemical parameters like nutrients, oxygen, BOD, suspended solids, etc. Then we take into account all the aspects that are related to biological elements, for example, starting from fish, mussels, benthos organisms, macrophytes, algae, and maybe also other elements. We assess what is the quality of each element, and then we combine the quality for whole group of elements. For example, for these biological elements, it's one quality. For physical-chemical parameters, it's also separate quality. And the third big part in this ecological water quality assessment is hydromorphology. And this was in previous planning cycles, it was not so deep covered. However, in the assessment, we see that actually all the changes that humans have made to our rivers, to our lakes, straightening the riverbeds, building different kind of barriers and other elements, also ports. It all changes the natural habitats. So because of these hydromorphological changes, also biological elements change a lot and the quality can be decreased. And so all these three big parts should be joined into one big assessment. And this is called ecological water quality. And as you see on the map, the biggest part of our rivers is yellow, which means that the quality is moderate. According to Water Framework Directive requirements, all our waters in lakes, in rivers, should be at least at good quality, at good ecological quality, which is green ones. And the best possible opportunity is if we can draw our waters in blue. It means that this is high quality, high ecological quality, and this impact of human activities is insignificant, or there is no human impact at all. However, we have also not so big part, but in orange and even red, which means that these waters are in bad or poor status. And of course, we should do something with that, not only assess the quality in general, but also make some consequences, implement some measures, and make some improvements. And now we are on the part where I will describe in very short how looks river basin management plan. So the most important part is monitoring. Actually, without existing data, we cannot assess the impact, the quality, and is it okay, or should we do something? So intensive monitoring, it's the best option to identify all the problem areas. Of course, as always in all spheres, we would like to have more and more detailed monitoring data. Not always this is possible, so we use also like aggregated data or data that are not so often taken, or maybe some older data even. It depends on data availability and the place and area and the requirements that should be met For example, on the river mouth and rivers on the border areas, there is very intensive monitoring in these sites. It's once per month, and this is to assess, for example, the impact of transboundary pollution and impact to Baltic Sea. These are also requirements regarding HELCOM issues and other transboundary issues and transboundary cooperation issues. If we know the monitoring data, the status, then we can also identify the pressures. So what is the reason for water quality not being in good status? And this is actually also a very complicated process because available information is very often not enough detailed, or maybe sometimes we don't have even idea or no data at all about some significant pollutants. We had such situation, for example, in Aģe River, which is a river which is very, very, very deeply monitored in Life Good Water project. Usually we have in monitoring one point on the river mouth, most usually. However, in the project we can have a lot more these sampling points. For example, in Aģe we have more than 15 sampling points. And so if we would look only on the monitoring data on the river mouth, then their quality data showed that the quality is between good and high status. So no problems. However, we knew from the pressure analysis that we have their hydropower stations, so barrier on the river. We have there some point source pollution, like wastewater treatment plants. We have agricultural areas around and other potential pollution sources. And after this intensive monitoring, we identified that in the same upstream of the river, there is very high concentrations of nutrients. And from where? It was from slaughterhouse. According to official data they were providing in Water2 database, there was no problem at all. However, in the real life, the water color was red with interesting smell, and concentrations of nitrogen, for example, was like about 200 times more than usual treated wastewaters. So you can imagine the amount of nutrients, and of course we saw this result also in the river. We solved it in close cooperation with State Environmental Service, but why I was explaining you that, because it gives you the view that not always these official data are enough to assess from where the pollution is coming. So the more detailed data you have, the more precise you can be. And afterwards, we have also economical analysis. This is to make to say what kind of changes we will have in the future. Will our economical activities stay the same as they are now in current status? Will the economic analysis, economic activity increase, decrease? How will change the population amount? Will there be some support to agriculture sector, or some maybe changes in taxes, etc., etc.? It covers a lot of issues, and I'm not specialist in this field. However, this gives some ideas where to looking for, and what can change, and how how significant these changes regarding economic activities can be, and how this can impact also the waters and all these potential pollution sources. After we know all this information, we can prepare a program of measures. And program of measures is aimed to reduce impact of significant pressures. And this is also quite not very easy way how to build this program of measures, because you can always choose a lot of options what to do. And mostly it depends on site. However, if we are talking about river basin management plans, we are talking not only about this ecological water quality and issues, but we are talking also about chemical water quality. And for example, here is the map where are pointed the sampling sites in 2022, so in the last year, where we took some chemical quality elements for the laboratory analysis. And on the map, we have colored the results depending on the substances. There are some samples are taken in water, and the results are shown then in green or red part in the cycles. It's in fish and also in mollusks. There's also these chemical substances are taken also for sediment analysis. However, on this map, I didn't find them made previous year. So what kind of elements are measured? These are, of course, starting from heavy metals, PAHs, VOX, pesticides, and other many elements. Usually it's regarding this chemical water quality is that if there is at least one chemical element in bad status, then all the quality in this water body will be bad. So, for example, if in Liepājā lake the fish samples are with very high, hydrogen, mercury concentration, then the quality, chemical quality of lake will be bad. So it's very easy to understand if you see on the map, for example, red dots or red color, then it means that something isn't good. And if we are talking about significant pressures, I already pointed some of the pressures that are analyzed. And we talk about three big parts, about point source pollution, about diffuse pollution, and hydromorphological alterations. In case of point source pollution, there's also two parts. It's wastewaters, and it includes not only nutrient pollution, but also this chemical substances pollution. And regarding contaminated sites, it's obviously, as Toms already explained, there's a huge spectrum of different elements, and we are using the information that is already available in this contaminated sites database. Regarding diffuse pollution, we are using a lot of data regarding agricultural pollution, agricultural areas, agricultural activities, animals, and many other aspects. Usually when I talk with people, they are surprised that also forestry areas make some pollution, because people used to think that forest it's a very natural area and there's nothing to worry about. However, if we are making there some economic activity like clear cutting or drainage, it all increases the amount of nutrients and also other elements that can flow from these areas. And third aspect is also very, for population, it's decentralized wastewater systems. And some parts of Latvia, some water bodies are also identified that they're one of the main pressures in these water bodies is these individual wastewater systems. So it means that not all the households are connected to centralized sewage network, and these individual outflows are quite significant. Especially it's in rural areas nearby the lakes, where also some kind of cooperatives are located. It's very interesting areas, and when you walk through the river, then you can see some small outlets flowing. So depending on the aroma, you can imagine what is there, what can you find there. And regarding hydromorphological alterations, we are assessing barriers. Oh, only 3 minutes. Okay. Barriers, all the changes that people has made in also in harbors, in polder systems, and with straightening with these regulations and deepening. And now about contaminated sites in our Latvian water bodies. When they are significant if the contaminants are already represent in artesian waters, and if at least 3 contaminated sites are nearby surface waters or in very close area. So on the map with the red dots, there are those significantly impacted water bodies where usually are more than 3 contaminated sites located. And then if we are moving forward to program of measures, then of course to solve all the problems you need funding, you need some money. And we tried to put together all this funding that is necessary to improve the quality of our waters. And in this graph, you can see that these are measures and amount of funding necessary to reduce nutrients in our waters and to minimize hydromorphological alterations. A lot of funding is missing, especially regarding agriculture and also obstacle problem on our rivers. Similar graph I made also regarding chemical substances and contaminated sites. And if we are talking about remediation of contaminated sites, then you can see that also a lot more money is necessary than is available. And similarly is regarding hazardous and priority substances that we would need a lot of money, but it's not strictly said where we will get this funding. So we don't know exactly from where this funding will come. Then we have also very interesting map and info. Later on, you can use this presentation and just click on this link. Yeah. No, you don't. Okay, below on the lower part of the slide. This is river basin management system. You can find there, for example, tirzniecības canals, and check the information that we have about this water body. There is starting from quality, from significant pressures and measures that should be done. Very, very significant information is regarding progress that is made regarding these contaminated sites. And one is updating of this environmental pollution information in database that Toms already showed. Then it's question about remediated sites. Is it territory clean enough? And it depends on the available resources, because not always you can clean absolutely the site. And it depends, of course, on environmental requirements. And very important is also to follow up the remediation process of contaminated sites, to make this monitoring afterwards, and to ask for us, are the waters safe enough? So I have this time already ended. So this is only one slide about Good Water project, and it's very, very connected to river basin management. And it's aimed to improve water quality in water bodies at risk. These are indicated on the map with this pink, and yeah, there's not so very good scene, but and we are aiming to reduce point source pollution, diffuse pollution, and minimize hydromorphological alterations. And of course, this monitoring, as I mentioned with the Aja case, is very, very important. So if you have possibility to have this monitoring, do it. So thank you for your attention. I hope that it was quite interesting and useful also. Thank you.
Thank you so much. What we just witnessed was an excellent cooperation between state organizations, because Toms in his presentation, he made it shorter, so Linda can use some more minutes. So it was an excellent exchange of resources, and in this time the resource was time. Well done. Next speaker, Jānis Bikše on springs as a bridge between science, water policy, and society. Floor is yours.
Hello. Yes, I'm Jānis Bikše from University of Latvia, and together with my colleague Inga Retiķe, we prepared a presentation where I will talk about springs and how can springs also help to assess some natural water status through citizen science monitoring. And basically, in this presentation, I will show how we have combined science, water policy things, and also how we involve citizens. Groundwater is really important in our world. Approximately 30% of all freshwater on Earth is in the form of groundwater. And basically, the rest of the water is actually in glaciers, and only approximately 1% is stored in rivers and lakes. So groundwater is really important for us. And even more, it supplies approximately 50% of drinking water in the world. And groundwater is a really nice thing because it naturally purifies or remediates pollutions, at least some kind of pollutions it can remediate, and groundwater is typically it's a clean water source. For example, as a denitrification. A lot of, for example, previous presentations dealt with the nutrients, and groundwater is a place where some of the nutrients, especially, for example, nitrates, can be really successfully denitrified or removed from water. And groundwater is really important also for all the surface water streams or lakes or ponds, because groundwater is at least in our region where we have more humid climate, groundwater is the most important thing that sustains these surface water systems especially during the drought periods. Or these are like groundwater is like a mitigator thing for climate change. So our surface water systems most likely will not suffer so much from extreme drought events due to groundwater. Oh, it was, okay, it changed. Yeah, and about springs, the springs actually is the only place where we can observe groundwater by our eye. As I said, there's a lot of groundwater under our ground, but it's invisible for us. And springs are the only places where we can see it. And there are different definitions for what is a spring or groundwater outflow, but in general, it is a place where this groundwater emerges to the ground, and we can observe it. But the form how these springs emerge can be quite different. There are a lot of, these are just a few examples how the springs might look like in the nature. Some of these types are more common for us, how we understand that, yes, this is a spring, but in some cases even the spring is not so visible, but we can see that there is a spring due to some ecological aspects, due to some specific plants, or sometimes only when we take some measurements we can understand that, okay, this is groundwater that has seeped out of the ground. For example, I will just tackle few interesting spring types or more common ones, and one is limnocrine springs that emerge in the ponds from unconfined or confined aquifers. And in Latvia, I think that one of the most spectacular spring of this type is in Ķemeri. It's close to the Riga, where we have this sulfuric pond where sulfuric-rich groundwater emerges in the raised bog. There's peat layers there where the groundwater rises, and due to gypsum that is located in these aquifers, it is rich in sulfur. So when the sulfur and organic material meet, then hydrogen sulfide is formed. So there is a lot of, there are many, quite distinct smell over there. You can like, it's like a rotten eggs smell around there, that place. And it's quite spectacular from hydrogeological point of view. More common spring types are these gushet spring types, where there was some fracture or fissure in the outcrop. For example, in Latvia, most common spring types are the ones which are located in Gauja National Park, because there are a lot of sandstone outcrops. And if you look more closely to these springs, basically all of these springs are formed where there is some kind of fracture in the sandstones. And this fracture is like has been like an initiator to water to go to outflow from that place. And these are the springs that most often also forms caves, also in Latvia. And the next thing what we are interested in are watersheds. Watersheds not for the rivers, but watersheds for springs. Because, well, this picture represents watershed, I know, okay, represents watershed for a river where we can observe by our eye that there are there are some tributaries, and we can delineate the area which is the area where the water comes from to this particular river. And basically the same analogy can be used also for springs, but it's a little bit more difficult because groundwater is not so visible as we already understood. And but if we can do that, if we can delineate watershed for springs, then we can tell some more interesting aspects. For example, if we know the geology there, we can also predict what could be the groundwater chemistry, or we can assess if this chemistry of the spring is correct according to the rock types there. We can also assess what is the land use effect on the spring. And moving from the land use, we can also assess anthropogenic activities, impact from nutrients, and also impact from point source pollutions. So if you find a landfill next to the spring, and if it's within this watershed, we can also suspect that there might be some problems in the water quality. And there are many benefits for springs. You don't need to install any monitoring location, because typically to monitor groundwater, we need to drill a borehole. We need to use, it's quite expensive, then we need to go there, we need to pump the water out, and these are a lot of costs. Springs are flowing all the time, they are there, we don't need to install these things. If you know the watershed, you already know what the spring does represent, what is the watershed. But there are, of course, limitations because we don't know. Maybe we want a spring here, but there is no spring, so we can just use the springs that we already have, and we need to map them. We need to find where are these locations. So I will show one example of one collaboration between scientists. So I'm representing University of Latvia. We were scientists. Between the people who are responsible about policy in Latvia, so Environmental, Geological and Center. Okay, maybe I've missed it. But between citizens. So we had a collaboration between Latvia and Estonia where our focus was transboundary area between Latvia and Estonia. We wanted to improve monitoring there using springs. And the first task was to map all the springs in this territory, and to do that we created a citizen science activity where a web portal was created both for Latvians and Estonians. Actually, the data and the database for these both sites, for avoti.info and alicat.info, is the same, only just some interface difference are there. And so we encouraged people to use this site and to map all the spring locations that they know, or maybe they can find some new locations. They could also enter observation. We also created the spring monitoring manual. It was created by Tallinn University from Estonia. And what we asked people to do is to find new spring locations, but also to make some observations. And that is the reason why there was these instructions, these guidelines. And some really simple measurements can be made by everyone. For example, if there is a good spring where there's, for example, some tube, you can make discharge measurements quite easily with your stopwatch in smartphone and some bucket. In some cases, maybe you have some electrical conductivity or temperature or pH meter, then you can also take these measurements. But one of the most important and one of the easiest measurement is actually photographies. And people like to take some photos nowadays, and it's also quite important to collect these photos from different seasons just to see how the spring looks like. For example, is there a seasonality for this particular spring? If we take pictures in 2 different seasons, definitely we can observe, even without any measurements, that there is some changes. And according to that, we can also suspect that there are some particular features for this spring. For example, if it has so strong seasonality, that most likely the water is coming from shallow groundwater. It's not some really deep water. This is like one thing that we can conclude from this observation. The next step is we have collected a lot of springs, and our task is to deliver to policymakers only few the best springs that represent groundwater. So how can we select the best representing springs? And one of the options is firstly to screen all these springs, just to select the best springs that we think that could be suitable for this task. So we did it. We selected more than 50 springs in this transboundary area, and then we just visited them. Latvians visited springs on Latvian side, Estonians visited springs on Estonian side. We did all the measurements in the same methodology. We even went out in the same day just to not have influence from different seasons or different weather conditions. And we collected a lot of sampling bottles, and even these samples were measured in the same laboratories. For example, water stable isotopes and trace elements were measured in University of Latvia, while major ions and nutrients were measured in Tallinn University. And again, all the samples and everything was performed in the same manner. And yeah, as you saw, really a lot of parameters that we used, analyzed. And the next step was to establish watersheds. I already told that it's really important to understand where the water comes from. And for springs, it's a little bit more difficult because we don't know always where the water comes from. But because of the groundwater chemistry, we have some indication if it comes from shallow groundwater or from deep groundwater. In Latvia, we have a situation where we have really huge, a lot of layers of aquifers, aquithards, and typically in hydrogeology, we just say that, well, it's really simple assumption, but we have these unconfined aquifers, that is most often quaternary aquifers, and then there are some deeper ones. And for these deeper ones, we had to create a groundwater model for this particular area because it's not possible to assess where the water flows without using any more sophisticated tool. So, for example, these blue areas are watersheds that are delineated using original groundwater model for this area, while the pink areas are watersheds for unconfined aquifers using topography. And the previous slide, there's one more thing. If we know the watershed area and we know the precipitation, evapotranspiration, or at least some estimate of evapotranspiration, we can assess if the water that flows out of the spring is actually theoretically possible according to this drainage area. So we can also cross-check or validate the results of our watersheds or our discharge measurements. And then there are some general results. When we combined all the watersheds, combined all the chemistry analysis, we ended up with a few distinct spring types. So this is one of the spring types that represents bedrock aquifers. So these are confined aquifers that are typically, at least in that territory, these are located in sandstones, Burtnieki and Arukila. These are basically middle Devonian sandstones. And the water has typical distinct chemical composition, for example, elevated barium, or some other elements are quite more or less distinct, and this water is really safe from pollution point of view because it's really protected from the upper part. Another spring type is unconfined, what we call these quaternary springs, or these are springs that forms from unconfined aquifers, and these are oxygen-rich springs where which has much smaller watersheds, which are located more close to the spring outlet. And these are the springs where the pollution has much more significant impact. And if you see some pollution really close to these kind of springs, then you can suspect that the pollution might be also present in the water. And that's not the case in the previous slide. If you see this spring, maybe there is a pollution next to the spring, but there is a possibility that this pollution cannot enter this spring because it's coming from deeper confined aquifers. But this is not the case. This is not the case in these quaternary springs. And these are typically in the quaternary sediments, as we in Latvia have. On the surface, in the first few meters, we have these quaternary sediments, and yeah, these are much less protected from pollution. And the final task is to include these springs in the National Groundwater Monitoring Network. And yes, doing all these modeling things and spring visits and analysis, and we also, to get these results, we also performed some statistical analysis and even some machine learning approaches to gather all these results together. And it ended up with a few selected springs, both for Estonian and Latvian side, which are most representing these typical spring types, for example, which are representing confined groundwaters, or which are more representing unconfined aquifers. Maybe the problem why I'm saying that not all the springs is not suitable for monitoring needs is because quite many springs have mixed water. one part comes from deep groundwater, one part comes from shallow groundwater. And even the proportions of these mixing factors can change over the seasons due to if there is a lot of rain or snow melt in the springs, then there is a one fraction of this between the deep and shallow groundwater, and in the summer it's a little bit different. But anyways, if we select the best springs and we know what it represents, we can use it in national monitoring network, and this is already established spring monitoring network in Latvia. Yes, in Latvia we already have springs in national monitoring network, which are in the with a focus on groundwater, of course. It's not the case in Estonia. So for Estonians, this activity that we performed was quite new, because this is the first time they are thinking about inclusion of springs in national monitoring network. But in Latvia, we already have 30 springs that are located maybe a little bit more in the Gauja River basin, because there are just more springs, and less in other parts of the Latvia. But even these springs already show some influence from agricultural activities, and we can see that, for example, there are some nutrients that are more present in springs that are for springs that represents fractured aquifers. In Latvia, these are dolomites typically, and a little bit less pollution in aquifers that represents porous media, like sandstones. And yeah, so we hope that springs will be like a really nice thing to include in the national monitoring program. What we can conclude from this, all this activity that we performed, that springs indeed are really important, and these can be really useful for monitoring needs. There are some limitations and also some benefits from them, but according to our activities that we did it during the project, so the project will end and maybe the scientists will focus on a little bit different things, but this citizen science approach, although it's working, there should be some funding available just to sustain these kind of activities, because maybe now we have one kind of result, but in the future, if citizens will collect a lot of more spring data and more observations, we can go through all these data again and find new ways how to use the data set to help our policymakers to monitor groundwater. Okay, that's all. Thank you.
Thank you so much, Jānis. Actually, you can already take the seat, whichever is the best for you. And please, Saya, take a seat, Toms and Linda. Now it's the time when we can start a discussion. And before we go further, I already have a question about springs and their basin. We know the river basins, we know more or less where they are located, and now you're talking about spring basins. Do they overlap, or it's absolutely completely different thing?
Most often these are different things, because springs are they are representing this one kind of springs represents much smaller area than rivers, and the other kind of springs, these deep confined aquifer springs, can represent much larger area than some of the rivers. And yeah, especially for the deeper springs, deeper aquifer representing springs, the watershed can be totally different than the surface water streams. Even the direction of the water can be totally different. So they are not the same.
Okay, thank you. I have a question for you, Saya. So Archipelago Sea, a lot of islands. Do people live on those islands? Do they have any human activity there? So is there any anthropogenic, let's say, nutrient flow from the islands themselves?
Yes, there is at the moment. Of course, in the past, people living on the island were living on the fishing, and later on with the farming. And now people are all the time moving more towards the cities, so farmlands at those islands are not that much anymore. But of course, when we experienced the anoxic conditions already back in time, like 150 years ago, and in this basin that I'm studying, like more than 100 years ago, this agriculture must have had an impact. Nowadays we have a lot of point sources on those sites, so there is a lot of fisheries and such, so yes.
Mm-hmm. And the people living there, are they willing to cooperate and to actually do something to change in their habits to improve the environmental status?
Yes, I think the general attitude is quite protecting and quite worried about, because people living in an island, no matter how few they are nowadays, they have, and usually these people are a bit older generation, so they have seen the deterioration and they are worried. But if your income is from fishery, it is difficult to stop it. And of course, it's a tricky issue, because the fisheries are a point source, but the largest problem is the legacy phosphor that is released from the sediments, and so it's difficult. But people are still, I think, quite good attitude for protecting.
I'm glad to hear. We have a question from a viewer from online. Rita Poikan wants to ask you, Linda, which are the main chemicals which are the main chemicals that you see that are contaminating river basins? Which chemicals do you find in your research?
Actually, I asked this question also to my colleague, and she gave me a correct answer. And the main elements are mercury and BDE in fish, as well as benzopyran and also mercury in water. And the results are very similar to all the Latvia. They don't dominate in one part or other.
Okay, so we don't have anything like the chemical of Liepājā or the chemical of Reizekne?
No.
Okay. Toms, I remember the slide on how the information collection and digitalization will happen. Who is going to pay for all the research? Will it be the owner of the land or anyone else? For example, I buy a piece of land and then bang, looks like a contamination there. I already spent all my money on buying the land. Am I in a deep trouble or?
Yes, unfortunately you are. But first, before you buy the land, you can, if we have a good data about the polluted sites, you can already see that maybe you shouldn't buy it. Or if you buy it for the purpose of, I don't know, manufacturing or something, you already know that you will have to do the research, have to do the remediation, and you can already plan the resources for that.
Okay, so here we have an answer to a question: who might be the potential clients of this information, who actually need them? For example, those who are going to buy a land to check out if it is actually...
Yes, there are actually many, for example, I don't know, before building shop or factory, many already enterprises do the research on their own just to know if there is no contamination. That is a good practice already in the industry, that they do that before, even if it's not in our registry. They just want to be sure. So yeah, it's a good place to start with the research already.
Are there any questions from the audience here? Okay.
I have two. Can I?
Yeah, please. Oh, I didn't see. Sorry.
You definitely. Okay, thank you so much. I have a question for the TWOMs. Is in this system will be available also historical data? So if you said it's potential maybe, and then they make assessment, and then it comes out that it is not, or maybe they make some clean up, and then this status is changing. So I, as a maybe potential buyer or whatever researcher, want to see, follow up maybe the history. This information will be available on the system?
Yes, first of all, there will be all the information that's already available in the existing registry. That is a base that you can already see. And if we add some digital materials or other information is updated on site, you can follow it on the system and use it.
Very similar question to Jānis. As well, is in this platform will be gathered the information from the project Dabas skaitīšana as well from this?
No, Dabas skaitīšana, this, I don't know, nature counting project is not connected to us, and it's our focus is springs.
In this project, what I mentioned, there was also for the experts a special part in the application where we could point out that there is a spring. So maybe just I wanted to know, is it somehow connected? Because mostly the experts have been worked through all the Latvia and pointed potential springs. Not potential, but existing springs, I'm sorry.
Yes, actually we have already used that kind of data for some specific tasks where we need to find any spring. Currently there's maybe the definition of spring is one, but another thing is how large spring is really a spring. For example, in Estonia, there is one researcher who's actually also involved in kind of similar Dabas skaitīšana project in Estonian side, and he maps everything where at least some small stream, not even stream, some seepage occurs. And when in Latvia, we don't have such enthusiastic person who will map all the small streams. So currently, at least in Latvian side, I will say that we have only these large springs. And in Estonia, we have more, as you said, these hidden springs in some bushes. And okay.
Thank you so much. So I can give up.
Okay, thank you. My question is actually maybe to the city representative that presented this factory, the water factory, but you might be able to answer. Is there, I mean, he said that huge amounts can be exported as from the groundwater. So is there any risk of that water being polluted? I mean, is it all from the blue sector, or is it partly from the green sector that I guess Linda presented? Or can it also be from the yellow sector? Or is there a risk that it becomes contaminated?
Is Emil's here? Sorry, all this is not here. Okay.
Yes, I will try to answer to your question. It depends on, the question is to water quantity. And we have also in river basin management plans assessed is the water quantity issue the problem for us. And currently we say that no, it isn't. However, in Liepājā city and nearby, there were, during the Soviet times, there was very intensive groundwater intake. And it caused this depression, how it calls? Yeah, so, and on the latest years, we see that these groundwater levels are slowly rising. So the problem seems to be solved or solving. And together with this depression cone, we saw that there was also intrusion of salt waters in groundwater, in these artesian waters. And according to monitoring data, also these concentrations are lowering, if I'm not wrong. Maybe, Jānis, you know, more precise.
Yeah, I have researched this, as I'm from hydrogeology, I have researched this topic a little bit more. Totally right, as you said, and yes, when the Soviet Union collapsed, and especially when this metallurgy complex that Uldis showed before, that this huge industry collapsed, water consumption drastically decreased in Liepājā, and seawater intrusion that has been formed here in the Soviet times, it was removed, so there was freshening process. But still, although groundwater levels are raised again and its general flow is to the Baltic Sea, still some parts in the central part of Liepājā, maybe even here, we have salty water below our feet because due to this former seawater intrusion. And if we will extract much more water due to this water terminal, there is a possibility that there will happen some similar things. As Linda said, I think that there will be no impact on surface water systems, but there will be impact on groundwater. But again, as we had this problem for quite many years, we have like reserve plants, or how to call. We have these water intakes located not in Liepājā city. These are located much further away from the city, just to stop these seawater intrusions processes. We have two intakes. One is next to the Liepājā lake, and one is even much further away from Liepājā. So we can minimize the risk of these kind of seawater intrusions.
It looks like it will not be the problem of water quantity, but if we look at this project from a wider perspective, then of course there are questions like, how does it make sense to spend all the natural resources like fossil fuels to transport it all the way to African countries and so on? There are many questions about environmental aspects, and definitely a very interesting project to discuss. Please.
Yes, I have a question for Linda. If we are speaking for polluted sediments, and we know that after remediation works we should achieve some legislation requirements. And we know that in Latvia actually we don't have specific regulations, and we normally use regular soil regulations, what is very strong. And in your opinion, do we need to have discussion in Latvia that we need to change the law and to have international experience? For example, in Norway, we know that there is a 5-level goal principles. And actually, if we are speaking, for example, for the Liepājā Karosta project, then our legislation demands to achieve the very high, this good quality results, what we cannot actually achieve. And is it maybe necessary to have such discussion right now that maybe this picture of polluted sites is not so optimistic if we are looking on the Latvia, and there can be work with legislation actually?
Thank you for your question. Actually, we had in previous years, my colleagues had common projects with to gain experience with this, how to solve contaminated sites problem and all these concentration limits together with Sweden, with Finland and Estonia. And actually, those limits are very okay. However, it depends how much we want to clean the site. It depends on the usage, for which reason we will use this area. If this would be continued industrial activities, of course, there should be question, do we need to remove all these chemicals till the level that there could be also built some kindergarten, for example. However, in Latvia, we don't divide these issues. And this question would be maybe more to be asked to Ministry of Environment, what is their opinion, because, sorry, I'm not legislation manager or...
Any more questions? Please remember, if you'd like to ask something in Latvian, feel free to do so. Okay, if there are no questions yet, as it looks like, I have a question for Saya. Let's go back to Archipelago Sea. A very interesting place with a very complex bathymetry. Is it actually possible to, let's say, to get rid of all the nutrients and to have oxygen-rich waters, taking into account this very complex water exchange and so on? How big impact of the situation is on the side of natural status, natural impacts?
Where to start? So, yes, I think there is chance, but we just need to understand as a society that it's going to take a really, really long time. So we already know that the eutrophication start to impact our oxygen levels on the deep basins more than 150 years ago. And it means we have a long run to go. Now the internal loading machine is up and running, and there is not like a stop button in that machine. So it just needs to use it full, and then it shuts down. So what is possible to do is to further reduce the internal loading, because it is still the problem that is further feeding the system. And of course, with the climate change, we got warmer water temperatures, and the warm water can incorporate less oxygen because of the temperature itself. So there is quite many problems, and I think this is like also a problem in communicating, because we see that we do whatever we can and reduce phosphor loading and everything, and still it's going towards wrong direction. So we need to better communicate that it will recover, but it's gonna take really long time. But we still have 2,000 years before we can walk on this soil. So I think there is a good future for Archipelago Sea, but we just need some patience.
But do you have any historical sediment data which would suggest that, for example, 500 or 1,000 years ago, there were no dead zones there?
Yes, we do have, and because of the sediment records, we know approximately the timing in such basins when the oxygen was gone. And we see from the sediment cores that it is happening quite rapidly. So the first it is like a massive sediment, and then suddenly things change within the course of 10 years or so. What we know and what we can see from the sediment records, it is also the impact of climate itself. So we have evidence on increased anoxia during, for example, medieval warm period that was occurring in the 1200s or so. But it is far from the modern scale. So there is natural changes, and because of the small and detached basins, they naturally are in the risk to suffer from anoxia in a seasonal scale or like centennial scale, but this is unprecedented what we now observe.
Mm-hmm. So obviously we have a proof that it is possible to have dead zones more or less free archipelagos.
Sorry?
I said that we have a proof that it's possible to have dead zone free archipelagos as it was
yes, exactly.
many
yes.
years ago.
We have
any
one more question is from the audience.
Also to Saija, in the area that you monitored, are there any fish farms there, and do you see them as a problem?
Yes, we have evidence on that. So in that area that I am showing to you, there is no fish farms in a close, but I have a colleague working like a next basin, and that is anoxic, and there is a fish farm right next to it, so we can see the impact of this point source. But that basin too went anoxic like 100 years before the fish farm. But from the sediment we can see the impact. And it is just because the basin is very small, so if you have a fish farm there, it's really focusing on that.
But would you recommend this thing that they put them on land-based basins instead of in the sea?
That would be a really great solution, because then you can manage the waters and remove the phosphorus that we anyway will need on terrigenous regions for cultivation. So, but of course I know that it is really expensive and it takes time to change such industry. But I know there are some dryland fisheries in Finland, and it looks promising, but the transition takes time.
Okay, thank you. Anyone else? If not, I have a question to Tuomas. The digitalized data on contaminated sites will be available for general public, right?
Yes.
Will there be any part of this data, any aspects of this data, which will be still not available due to maybe security reasons, or can you imagine anything that general public should not see?
Well, yeah, we have to also evaluate and assess all the information and the levels on which we can open it. Of course, if there are like documents from the enterprises which are doing research who has a commercial secret or information about their methods that we don't publish that part, we would publish all the information which is basically safe to publish, and due to we'll have also a part where you can access the information. Those who want to access it, they can, but it will be like not in a public portal, but in an authorized space.
Mm-hmm. So I have to apply that I would like to access the data, and then...
Yeah, if you will want to have all the data, and yes, maybe then we can. But also, this process could be quite simple. That you just need to log in with. You don't need any specific
3 job interviews.
Yeah. You don't need to go through a complicated process to get this data.
Okay, thanks. Linda, in the map of ecological water quality, we saw that most of Latvia is moderate, and that there are some good parts. The low quality is Zemgale. How do we look in Europe? Are we the good country or the bad country? Where are we?
How to say? In average, our waters, only 33% are in good quality, good or high quality. Average in European Union, this number is 40. So we are a little bit below. However, these measures that we can take those are mainly in these yellow colored parts, so moderate, where we maybe not only not so costly, however, they can be very effective to improve the quality. And mostly these measures in these moderate quality waters are aimed to reduce nutrient pollution from agriculture in most cases, and to improve this hydromorphological alteration status. So usually this means removing barriers or lowering the impact of them, as well as make some environmentally friendly solutions in drainage systems and drainage system management process. So there are some solutions that will not cost some milliards of money, but the progress can be seen quite fast. Mm-hmm. The question is, are we ready to do this? Because we had recently discussions regarding barriers and what is the opinion of landowners or population that lives nearby such barriers that are built some 50 years ago, some more. And most of people says, yes, I agree that their barriers are removed, just not in my place. Please do it somewhere else. I don't want to be the first one that does this. And then we are talking with people that, okay, this barrier, for example, has been there for 50 years. However, before, some more than 2,000 or 9,000 years, the river was free-flowing. So who is responsible for that? Mm-hmm. So these are, of course, rhetorical questions, but we can do a lot of good things to help our waters.
Okay, thank you. Jānis, you mentioned that 1,165 new springs were collected, right? I have no idea, in total, how many springs are there in Latvia, or how many springs do you know in Latvia?
Most of these new locations are from Estonia.
Okay. Okay.
Because Estonians somehow are more active in finding new springs. They have quite nice history about springs, and they already have quite good database, and somehow we think that Latvians really like springs. I think Estonians like springs even more. And
come on, everything is better in Estonia. That's like a general Latvian thing.
Because out of these 1,000 springs, most of these are from Estonia. Yeah. In Latvia, much less new springs are mapped.
For a non-specialist, for a general citizen, is it easy not to get confused and to notice that this is a spring, not a small river or anything else? Are there often mistakes in this, or that's no-brainer? It's a spring, and everyone knows that.
There might be some cases when it's not so visible if it's spring or not, because even we have some streams that hides underground and then emerge in new place, so it's like a spring, but actually it's a stream 1 kilometer from that. But in most cases, these typical springs are quite easy to understand that these are springs, and in some cases, springs can be mixed with drainage pipes. So you need to check some drainage maps, because there have been some cases that when people think that it's a spring, but actually it's a drainage pipe.
Mm-hmm. Okay, thanks.
We have one more question from the audience.
I have a question to Jānis. You mentioned a nice example how citizen science can be involved. So I would like to ask, did you make any conclusions or notice what was a typical citizen scientists in your case? Was there like more men, women, kids, family with kids, old people, younger people? Who is eager to take part in citizen science in Latvia?
We don't collect so much so personal information, but we have some idea. there are a few, I will say that there are a few key people who are really interested in this citizen science, and they map a lot of springs and visit a lot of springs. And these are the few, I will say these are just few people in Latvia and Estonia which do the most of the work. And then there are some people who are just taking just some observations or just map some spring next to his house. And then there's another group of people which are basically classrooms when a teacher is hanging, taking out the children, and then they are visiting a lot of children in one place, and then there is a lot of observations from one place. So these are the main categories of visitors.
So these few people are already the scientists.
Yeah, I guess it's a nice way how to get little students interested in natural sciences to go outside. Doesn't matter if it's a spring or a forest or anything else. So that's real deal. Go outside. Any more questions? If not, then I invite you to go upstairs.
No, I'm sorry.
Sorry.
I will make some interruption. We would like to thank you to the speakers before the lunch.
Exactly.
Thank you.
Exactly. But maybe there was a question. When and where there will be
Yes.
the lunch? It's the 6th floor, and you have to be back at 1:30. But of course, thank you for your presentations, for the discussion, and for being very precise with time. I appreciate that. And also those who are joining us online, 1:30, and we are continuing with presentations and discussions. Welcome back, everyone. So we are continuing with our conference, but before we proceed with presentations, we have to talk about food. Many of you are staying for tomorrow as well, which is really nice, and many of you will want to have some lunch tomorrow as well. Please fill these papers to point out which kind of food you would like to have. I'll just give these papers around, so take care of tomorrow. So yes, now we can proceed with our presentations, and I'd like to remind you that everyone who is watching us online, please feel free to comment and ask questions. And those who are here, please, during the discussion time, don't be shy and ask and comment. I would like to invite Marta Barone. She's going to talk about something small but mighty, microplastics. The floor is yours.
Good afternoon, everyone. My name is Marta Barone, and I'm a research assistant from the Latvian Institute of Aquatic Ecology, where I also work on my PhD thesis about a very recent pollution type, which is microplastics. This one? To understand microplastics, we have to start with a bigger object, which is plastics in general. They are synthetic materials which are based on the resources they're made of. They can be divided into either synthetic or semi-synthetic plastics, which are derived from either non-renewable resources or renewable resources. And plastics, the best part about plastic is that it's very cheap, it's durable, and therefore it's widely used in the everyday life of almost all modern humans' life. Plastics mass production began in the middle of last century when it was advocated as a super material. It relieved the lives of a lot of housewives that no longer had to do the dishes. It improved the quality of medicine, the safety of food, and it skyrocketed the industrial sphere. The largest, since the beginning of plastic, they started making plastic, there have been almost 8.3 million metric tons of plastics being produced, which can be compared to almost 1 ton of plastic per each person currently living on Earth. And since the year 2000, almost half of this plastic has been made, and it's not predicted this growth of plastic production is not predicted to slow down. The largest producers of plastics are located in Asia, followed by North America and Europe. And this materials is mostly used for packaging and more specifically for single-use packaging. But the plastic itself is not the bad player in this game. It's the end of the life moment when the plastics enter the environment, and because of poor waste management. There are several countries that are responsible for most of plastics pollution going into the oceans. But it's worth noting that at the global scale, we can't make one country guilty of it, because as soon as the plastics enter water environment, it can be transported long distances and moved all around the world. In the oceans, there are 6 places, like hotspots, where plastics tend to accumulate because of the water currents and rotation of Earth. And one of these gyres or plastic islands are located in Arctic, and Arctic is kind of a perfect place for plastics to sink, to accumulate, because of the water currents and air masses are moved in the polar regions. Recently, Latvia's Ministry of Foreign Affairs applied to become the observer of the Arctic Council and committed to study different aspects of our Arctic region. And our institute, the Latvian Institute of Aquatic Ecology, undertook to study microplastics in Arctic. Recently, we started a project together with Iceland and Finland, with partners from University of Iceland and the University of Turku, to study microplastics in both Latvia and the Icelandic Sea and lake water and sediments. With this project, we aim to understand the extent of microplastics pollution in these regions, as well as exchange knowledge between partners at an international scale, which provides us the opportunity to share both knowledge and infrastructure that is not available for each separate institution. About microplastics in general, the definition of microplastics is that there are particles smaller than 5 millimeters in every dimension. And they can, based on their source, they can be divided in either primary and secondary microplastics. Primary microplastics are intentionally produced in this size, and they enter the environment already as microplastics. While secondary microplastics, on the other hand, are those which break down in the environment. They are created in the environment due to factors such as UV light, like physical degradation, biological or chemical effects. Microplastics are used in our daily essential products due to their stable chemical bonds, and due to this stability, they are hard to degrade in the environment, and therefore they stay there for a long time. Pathways through which plastics they enter the environment are very diverse. They originate either in households or industries of all kinds, and they get transported through rivers, water, like land surface runoff, air masses, or directly in the sea from shipping. And a big portion of these microplastics go through the wastewater treatment plants, from which the majority are not suitable to retain this kind of pollution. Recently, a few years ago, my colleagues did a study, an experiment, to understand how much regular user at home can create microplastic pollution, how much it gets created in the household washing of textile. And the study was funded by a company, Swimby, that produces 100% recycled swimsuits, and they wanted to learn what are their impact on microplastics pollution in the environment. So together with them, we created an experiment design which consisted of washing swimsuits either as they are, or using microplastics retaining bag, or washing detergent, or both of them. And the result, then we filtered the water that would normally go to the sewage system, and we counted how many particles are there from this one exact swimsuit. The results of this experiment prove that regardless of the type of the wash, either by themselves or with a bag or with a washing detergent, most particles were released after the first time of washing this garment. And we speculated that it could be, since no one has used this swimsuit, it's most probably because of the fibers that are have been created during the manufacture of the material itself, not the use or wear down of the garment. We also found that the microplastics retaining bag was unable to retain completely all microplastics particles. They got portion of it, but the smallest ones, they seeped through the holes of the bag. And washing detergent provoked the transport of microplastics through this bag, so it's better to use either only washing detergent or only this microplastics retaining bag, but not both at the same time. And the solution that Swinby also suggested to other companies and implemented themselves is to wash their products before giving them to consumer, to stop this first washing time, microplastics getting released to the sewage system, getting into the wastewater treatment plants that are unable to retain these particles. So yeah, this is about source that could potentially occur in household, and continuing about the pathways, how microplastics are transported through the environment. We studied rivers, because rivers for many countries, for many places, are the vectors. Like in the rainy season, plastics are washed down the river, enter the sea and beaches and bigger watersheds. But in Latvia, the rainy season is not so distinct. So we wanted to find out whether there is a seasonality aspect in microplastics pollution going through the rivers. Last year we studied the 4 largest rivers inflowing in the Gulf of Riga, and each of them have different industries in their catchment area and with different pollution levels. First I want to mention that these scales are on the y-axis, on the vertical axis are not the same, so please don't compare them directly. There are different seasons. In April, we collected samples in April representing spring, June and August representing summer, October representing autumn, and December representing winter. And we found out that more microplastics were, in most cases, were in summer season, either beginning of summer or the end. And one exception was River Salaca, where we found exceptionally high contamination levels in the spring, where many small rubber particles were found, and we speculated that it might be either from the old bridge crossing the sampling, closest bridge crossing the almost sampling point, or the port like buffer barriers, so the ships wouldn't bump in the board. They're also made of rubber. So we speculate that this might be from one of those sources. Dominant polymers that we found in these rivers were polyethylene and polypropylene, which also coincide with those globally most produced. And dominant shape for these particles were fragments and fibers. Yeah, so the sea is mostly either lakes or the sea are the recipients of microplastics that are carried through rivers. And in 2018, we initiated a study to understand how much microplastics is there in seawater. So we covered the marine area of Latvia as good as we could, placing the sampling points near potential pollution sources, rivers, ports, and also further away. And what we found was that microplastics were more abundant near the coastal area, and the concentrations of pollution decreased with the further away from coast the sampling points were. And also similarly, since the Gulf of Riga is semi-enclosed with a slower water change, the Gulf of Riga had also higher concentrations of microplastics than the open part of the Baltic Sea. Last year was kind of big for microplastics at our institute because we got a task to undertake monitoring of microplastics in marine water, and it was continuation of previously mentioned studies. Sorry, this was the slide about the concentrations that closer to the shore are higher concentrations than in the middle. So I think I might have the first version of the presentation, not the last ones that I sent. Yeah, I will continue with a not updated version. So last year we were allowed to start the monitoring, and we found out that the differences between the year 2018 and 2022 were in some of the spots where previously in this year there were quite low microplastic concentrations. Then last year, 4 years later from this, it was up to 40 times higher. So that proves that it's not enough to take samples only one time, especially with microplastics in the surface water, because the weather can change a lot and it impacts the amount of plastics on the top of the water. So the beaches connect us both, since the source and the sink of microplastics, because it's the closest area to the closest terrestrial area to the marine environment. And a few years ago, we conducted a study to understand how much plastics are there on Latvian beaches. So we took 24 beaches that are either the biggest ones or the most popular ones among the society, who used more for tourism. We took samples, analyzed them, and found out that we wanted to find out whether there is any correlation between the usage of the intensity of usage of these beaches and the microplastics concentrations, as well as whether there are some factors impacting the amount of plastics on those beaches. And we learned that plastics were more on those beaches where the sand grain size is bigger. So the bigger were the sand or rocks, whatever is on the beach, the more plastics there were. And this was especially prominent with fibers that were a lot more on those beaches. But we didn't find any evidence that tourism would impact the amount of microplastics there are on the beaches. I'm sorry, this is not the final version. I sent it, so there will be like unfinished slides and missing slides. Yeah. So there was. We also studied microplastics in lakes, which was the first freshwater environment we stepped our foot into. We took 3 lakes with different pollution levels. The proximity from cities, from urban areas. 1 lake was protected, 1 lake was, let's say, semi-protected, and the 3rd lake was in the urban area. And we took the sediment course, split it into layers, dated each layer to understand how old it is, and then we analyzed the respective layer for the microplastics content. And what we saw was the first thing we predicted to be as it was, that the more recent sediments had more microplastics in them than the older ones, located deeper in the ground. But what we didn't expect was that we will find microplastics in layers that are older than the time when plastics production began. Because we found plastics in sediments dating back to 17th century, 18th century, when plastics wasn't even invented. So we wanted to find out what made plastics be there in those sediment layers. did some statistical analysis with different factors and revealed that the most convincing factor was particle shape. Since more rounder particles were located deeper in the sediments than the elongated ones, which might be because of the surface area of particle that promoted the particles' migration through the sediment grains and deeper in the sediment core. And I will move to this slide. We have been studying microplastics for 4 years already. This is the 5th year. And we have developed quite good skills in samples treatment and analysis. But to move forward, we plan to advance our analysis methods to be able to analyze smaller particles, because most of these that I presented are starting from either 100 microns or 300 microns. And we plan to analyze even smaller particles. And the next step for us would be to study microplastics in living organisms or find someone to collaborate with to do so. Thank you for your attention.
Thank you, Marta. I'm sorry for the technical problems. But thanks for your presentation, and we'll keep on discussing during the discussion part. Now we will listen to our guest from Norwegian Institute for Water Research. Sissel Britt Ranekle will talk about how to identify the most contaminated sediments along the coast of Norway.
Thank you.
Right, so yours.
Thank you, first of all, for inviting us to come here and give a presentation. And we're glad that we can do that. And I'm from Norwegian Institute of Water Research, and we are a non-governmental, non-profit organization. But we have quite tight connection to the ministries, because we have some work that we have to do every year, and then we get a kind of funding from this. And about 25% of our funding is from the Ministry of Environment. So we have a tight connection. Here I will present work that we did on behalf of the Norwegian Environmental Agency, which is controlling all activities in relation to the environment. This work was done together with my colleagues here at NIVA, and also with from Aquaplan NIVA, which is a daughter company situated in the north of Norway. So here I will tell you the 24 highest concentration area of contaminants in Norway, the competition, who is the winner. So my speak is divided in 3. First, I will tell about why we did this. The second, I can tell you a bit about the method we used. And third, I will tell you the result of these 20 sites, of the most contaminated sites in Norway in the sediments. So this is the situation in Norway today. We are a sea nation. We have one of the longest coastline in the world. We are only beaten by Canada. And from the south of Norway to the north, it's a distance that goes close to the south of Italy. And most of the people are populated along the seaside. And we have a lot of activities in the seaside because we are quite a hilly, mountainous country, and transportation and industries are very often situated along the coastline in the fjords. This is also due to that the energy is quite cheaper or available from the river that are quite steep and ends in the fjords often. So today, the maritime activities, if I account for the platform, the oil industry, it's close to 100% or of the Norwegian income comes from activities on sea, actually. And due to that, we have long time activities in the sediments. The sediments are, of course, polluted. We have traces of human activities in the sediments. So we have a list here, old sins, today active industries, shipyards, harbor activities, maritime activities, offshore activities, and of course aquaculture. Norway has a long tradition for using sediments and monitoring of sediments. Early in the 80s, we discovered that we had high concentration of polyaromatic hydrocarbons, tar substances, in the sediments because we have a lot of aluminium smelters along the coast. So early in the 80s, it was discovered that we had a lot of contamination, especially from the aluminium industry. And then in 89, we started to make action plans and description of the problems from each site. And in 2001 and 2002, the government made national goal for remediation, and we made action plans for 29 counties in Norway, from the south to the furthest north. And in 2006 and 2007, we made national action plans for 17 prioritized areas. As you see here on the site here, some of these sites have been through a remediation process. Some have started but not completed, and some are probably not to be remediated before we stop the pollution from the catchment into the fjord. So this is the situation today. And on our national budget, we also have activities every year for remediation. That's one action plan for one action on just remediation of contaminated sediments and ground. So Norway has spent a lot of money and activities on this, actually. And when we got this project, it was finished in last year. There was a need for updated overview of areas and get new knowledge of new sites to be considered for remediation. Yeah. And as I told you before, we had a long tradition for monitoring in the sediments. And the Norwegian Environmental Agency have developed, together with, for instance, my institute and other institutes at NIVA, guidance document for handling of sediments. We have this holy Bible here that my colleague Sigurd will talk about later, risk assessment of contaminated sediments. We have guidance on handling of sediments, and several of these documents are also in English, actually. And we have a summarized report, for instance, about how the capping of the sediments. Usually we do dredging, removing the contaminated sediments, but also in some areas we have covered the contaminated sediments with fresh, new, uncontaminated sediments. And Norway is spending a lot of money on this, so we have kind of economical calculations of what's the effect of these remediation activities, and what actually comes out of this socio-economical consideration about all the money that we actually spend on this. So far, Norway has spent 0.1 billion euro on contaminated sediments and remediations from the start. And in 2007, the EU Water Framework Directive was implemented in Norway. Since Norway is not a part of the European community, all regulation usually comes a bit late to us. So in 2007, the EU Water Framework Directive was implemented in Norway. And after that, there was a huge shift in how we have to handle our water bodies, and we have had a lot of activities and preparing of guidance document for this. And especially this document here, EQSs, and classification of contaminants in sediment, water, and biota. This is one of the documents that we use quite a lot during our work to consider the contaminated sediments. So, as Linda, she's not maybe here now, she showed also these 5 different classes. And according to the EU Water Framework Directive, you should have good chemical and good ecological status to achieve the environmental objectives. And previously, we have this EQSs that was derived statistically, not effect-based. But when the EU Water Framework Directive was implemented, we got these effect-based EQSs for priority substances, the substances that the EU imposed on us to monitor, and on the river basin specific pollutants, the substances that are considered of concern to the Norwegian environment, and this is imposed by the Norwegian Environmental Agency. And in Norway, for the sediments, we have derived 5 classes. And you see here, if I measure a concentration here, that's the background level, and class 2, it's what we call PNEC, possible non-effect concentration. Pardon? Oh, sorry. So we have 5 classes, and if you have concentration in the sediments here, it's a chronic effect on the biota, and class 4, it's acute toxic. So if you measure a concentration in class 1 or 2, the good chemical or good ecological status with respect to the priority and river basin specific pollutants are achieved. And this was actually used for how we found the most contaminated sites along the coast of Norway. So, as Toms showed earlier, we have a lot of databases, and one of these is this Vannmiljø database. This is the sea outside the fjord, outside the Oslo Centrum, and here you see the blue. They are monitoring stations for sediment, for biota, for nutrients in the water body. And we actually, in the process here of how to find the most contaminated sediments, we went through this database, Vannmiljø, and looked for concentrations of contaminants in the sediments. And the Norwegian Environmental Agency has a lot of quality criteria that we have to consider when we did this. First of all, the sediment should be maximum 10 centimeter deep, and it should not be data prior to 2007. And the methods that has been used for taking off the sediment, analyzing the sediments, were supposed to be according to the guidance Norwegian Environmental Agency have been working on, or the guidance document they have provided. And we also have here some kind of number of stations per square meters. And the parameter of relevance was the priority substances and the river basin specific pollutants. And also in this database, we have the supporting parameters like concentration of total organic carbon, size fractionation also, and also the analytical method. Working with the contaminants like this, it's very important that you use a laboratory that has very low limit of quantification methods using that. So that is very important. So this was the quality sets criteria described by the Norwegian Environmental Agency. So first of all, we looked in data in this Vannmiljø database, and then we considered concentration above class 2. If there were concentration, no concentration above class 2, then we did no further action. But all the concentration above class 2 went to a quality check of data, because we also found that there's a lot of not good data in this database. And after a quality check, then this data went for further assessment. We also noticed that we also did not have we also had some data not in this database. A lot of the municipalities had, for instance, data in their drawer in the office, and this data had to also be considered. And then we looked through that data. And when the data was not acceptable, then we did a further deep down later in this data. So how did we actually continue from here? 135 areas were identified. We looked at the river basin-specific pollutants and the priority substances according to the Water Framework Directive. And we did not look at the TBT. TBT is used as a substance to prevent biofouling of ships, and today it's not allowed to use it anymore, but the whole coast of Norway is contaminated by this TBT. So it was not included in the assessment. So we looked at the concentration, this concentration ratio. The concentration CM is the concentration measured, and EQS, that's the EQS, class 2. So we took the concentration measure divided on the EQS, and then we made a summary substance concentration for each area. So we summarized all the substances that were above the EQS and the level it was above EQS, and then we got a number. So based on this, we have this. Since we were only handling substances that were exceeding the EQS, we are in this problematic area here, and then we ended up dividing them in 3. So altogether, 1,924 sediment stations were assessed. 82,891 single measurements were used for the calculation of this substance. Sorry, it should be substance. Concentration, this SSC. 80 areas were identified, 38 areas with SSC more than 10, and 20 areas were presented, and a fact sheet was generated from each site. So, then to the results, and here you can see the map, or the vannmiljø database, and then we have added other maps on top of this. Here you see the contaminated ground, here. And here we have the lines here. They are tanks used for storage of oil, for instance. And like places we have aquaculture, that is not here. And this square here, this diamond here, it's triangle, I mean, sorry, it's ship site for construction of ships. And this area here, you see that's a place where it's important for breeding of fish, natural. And so we made a lot of layers on top of this vannmiljø data map. And then we found the different sites. So here, this is the 20 sites that had the highest concentrations of the summarized concentration of substances. And here, as the most contaminated one, is on the west coast, Skiftisvika. Then we have had a high concentration of PAH, and this was a previous tar production site owned by the municipality, and it was also used for making asphalt. And the second here is the PAHs, and there's an aluminium smelter in the fjord. And the third is Saudafjorden. There is also PAHs and ferromanganese production. And Spjelkavik, Kjørsundet, also on the west coast. Most of these sites are actually on the west coast. And here there is a company that has been producing expanded polystyrene, and they have embedded the polystyrene with this polystyrene is used for construction, insulation, and they have been embedded with the brominated flame retardants to stop them for burning. And Florvågen here, no, Kristiansand, Inner Harbor, then it's a mixture of everything. You have a lot of shipyards, you have aquaculture some places, and it's an urban area also. And Florvågen, this is one of the also quite contaminated sites, and there has been a painting factory here. And Svolvær Harbor, it's a harbor and a shipyard. And Karmsundet at Bygnes, that's PAH and their PAHs, and there is also aluminium production and other activities. And Vegsundet is a shipyard and PAHs. Langevåg also on the west coast, shipyards and PAHs. And Orkdalsfjorden, metals and PAHs. There we also have a mine, but it's also a mixture of other contaminants. Fagerstrand, Aspån, there high concentration of PAHs, and we have a lot of storage of oil tanks and oil activities here, and Gansfjord. And also, let me please also say, notice this is the first site we have this PFAS. Usually we have not measured a lot of PFAS in the sediments, but here PFAS was one of the highest concentration. And here we have previous platform constructions, and it's a quite urban area at this one part of the fjord. And here you also see the shipyards, and usually there's a lot of mixture of contaminants. And here in Sandefjord, probably you have been using Jotun painting. So this is a dump site where they have dumped old paint from previous. And Samfjorden and Brattvåg, also shipyard. And Bodø Harbor, you have a harbor and also a shipyard. So these were the most contaminated sites in Norway. And today, some of these sites have started actually to clean up, like this, for instance, this area, Spjelkavik, Tjørsundet. This is in Norway. It's based on the polluter pay principle. So this is, they have not started with the remediation of the contaminated sediments with brominated flame retardants on the industry. So in the industry at this site has to pay, but in some places there are not well known who is the owner, of course. So then the Norwegian Environmental Agency then provide monies for remediation. Yeah. Okay, thank you. This is everything I have, and thank you to my colleagues and friends. Thank you.
Thank you, Sissel. And we are proceeding with Natalia Sukhareva from Latvian Institute of Hydroecology, Aquatic Ecology, biotransport of hazardous substances in the coastal waters of the Baltic Sea from Jūrmalciems, which is not very far from here.
Yes. Hello. As it was said already, my name is Natalia Sukhareva, and I represent the Latvian Institute of Aquatic Ecology. And there is a lot of thought about water and sediments, and now we will talk about biota. A little background first. Baltic Sea is highly polluted sea, and the main hazards there are, from the point of pollution, mercury by polybromated biphenyl ethers and polychlorinated biphenyls. First two have high concentrations in biota, and that's why Baltic Sea cannot reach good environmental quality yet. PCBs have concentrations which for now are lower than this good environmental quality standard, but this group still is considered to be problematic. All three groups are persistent, bioaccumulative, toxic, and tend to biomagnify in the food chain. Yeah. Should I use another one? Okay. In this presentation, I will mainly focus on two places. It is Jūrmalciems, which is located like 25 or 30 kilometers down to the south from here, and Lake Liepājā, but I will touch also other sites a little bit just to make the story more clear for you. The main character of the story or the model organism is European perch. It is predator fish in our waters, and is highly distributed in Latvian sea coast and also in the inland waters. Together we collected like 500, a little bit more, perch samples in Jūrmalciems and more than 100 perch samples in Liepājā ezers, Lake of Liepājā. And the first concern about that something happens there was already during the national monitoring, because annual variation of mercury concentrations in perch samples was too high, and it couldn't be explained by different pollution loads, because mercury is persistent pollutant, and it stays in the environment for a very long time. So a little bit less pollution in some specific year cannot affect it so much. As well as a part of the main trends of the contamination in the perch population, there always were some outliers which had much higher concentrations of mercury in the same length groups. So the question was, where does it come from? That's why we hypothesized that probably those individuals come from different sites, from other sites with higher pollution loads. But how to prove it, how to check it? That's why we took one case study, which is not here from Jurnmociems, but it's a good example to explain how it works. It was, It was Daugava, Kišezers, and Gulf of Riga. So 3 sub-populations of perch, but in totally interconnected ecosystem. And we checked ratios of stable isotopes of nitrogen and carbon. And it helped us to define 3 different population groups of the perch. But the problem was that there always were some individuals with mixed up signals of the isotopes. The method of type of isotopes works very simple. If you look on the horizontal axis, is nitrogen isotopes, then it shows you trophic position of the individual. This means that the diet of this individual changes from, for example, some crustaceans, then it takes lower trophic position, to fish, which means that the individual which eats fish takes higher trophic position. And if you look on the horizontal axis, it is carbon, then it shows you where did this individual was feeding during the latest months, more in the freshwater ecosystem or in marine ecosystem. So this principle helped us to identify this specific group of the mixed group of perch individuals who showed different isotopic signals from the place of catch. And there was approximately 40% of individuals who showed different isotopic signals. So having this background and knowledge and methodology, we came to the Jurnmociems case study. And first what we did, we sampled different populations of perch along the coast of Kursuma coast. This picture is messy, but I will try to lead you smoothly. So we sampled Venta, which is on the north of the coast. We sampled in Lake Liepājā, which is here, right, in Liepājā. We sampled Saka, which is just in the middle, and even Kuronian Lagoon, which is in Lithuania. And of course, we sampled Jurnmociems. And in Jurnmociems, we sampled perch in different months, like once per month, from May to September. And as you can see on this graph, the Jurnmociems groups is elongated towards the freshwater ecosystem. And only September samples showed clear marine isotopic signals, which is smoothly supported by the isotopic signals of other organisms, local organisms, for example, crustaceans, shrimps, for example, and marine fish species. At the same time, there is some perch from Jurnmociems who were caught in July and June and showed clearly freshwater signals. And on the other hand, there were some perch individuals caught in freshwater ecosystems who showed marine signals. And when we checked exactly the interaction between Lake Liepājas and Jūrmāciems, we found that there were like 40% of marine signatures in lake samples and 5% of freshwater signatures in marine samples, which is in line with the results I showed previously for the Gulf of Riga. So when we checked the concentrations of mercury in Lake Liepājas and Jūrmāciems, we found quite traditional classical picture that the concentration rises together with the length of a fish. And it was expected the concentration in Lake Liepājas will be higher than in Jūrmāciems, so everything nice. And the only thing is that later, like bigger individuals in Jūrmāciems reach approximately the same concentrations as they are in Lake Liepājas. But it also can be explained by, for example, shifts in the diet. In the stomach content analysis showed that bigger individuals almost completely switched to the most polluted food items in the Jūrmāciems. It's like big shrimps, relatively big shrimps, and round goby. But when we, mercury, if I can say like this to the hazardous substance, it's very nice pollutant because methodology of analysis of mercury concentration allows us to measure concentration of mercury in each individual, which gives us opportunity to trace the pollution along the population. If we talk about PBDEs and PCBs, then it is not possible. The methodology requires big sample weight. So we are forced to put together a lot of individuals, and it excludes the opportunity to follow the contamination along the population. But we can check trophic magnification. To do so, we analyzed 5 different size groups of perch, from the smallest one, which is below 13 centimeters, to the biggest one, which is above 22 centimeters. And we found that almost all PCBs and PBDEs show negative trophic magnification along the grove of the perch. Jūrmāciems here is the red one, if you see the colors. And we compared it to another sampling site, which is also on the sea coast, but in the Gulf of Riga, and it showed that in case of Salacgrīva in Gulf of Riga, it is not happening like this. So it is site-specific, it's specific for Jūrmāciems. And it cannot be explained by feeding ecology anymore, because if we compare feeding ecology of these two sites, they are almost similar. The components are the same, the difference is only proportion. So to understand what is the clue and what is the cause, another fish species came to help. It is smelt. Smelt is andronomous fish species, and the ecology of smelt says that it comes to spawn, it is marine species, but they come to spawn to freshwater body, and smelt juveniles spend the first year in the freshwater ecosystem, and in the end of the summer or in the autumn, it goes back to the coast where we caught them. So the concentration of PCBs in smelt juveniles in Jūrmāciems show concentration in some freshwater ecosystem, and the concentration was higher than in the biggest perch in Jūrmāciems, which is strange. And we cannot point out exactly which water body it is. We can only speculate that it can be the closest one or the most polluted one. And of course, we look on Lake Liepājas, because Lake Liepājas is surrounded by industrial area, urban area, and it has high pollution loads. So we measured PCB concentrations and purge in Lake Liepājā, and it was 1.5 to 3 times higher than in any other fish group, in other purge group in Jurmauciums, which again shows high pollution loads in Lake Liepājā. And this means that higher concentrations of PCBs in smaller purge and Jurmauciums probably come from some freshwater ecosystem, and maybe it is Lake Liepājā. But again, I don't have enough evidence. I have only some proxies. But what happens with PBDEs? Previous studies and also this study showed that PBDEs, like the composition of the most dominant PBDE congeners, is different in different matrices. What is congeners? PBDE, it is not just one substance, it is a group of substances with approximately similar chemical properties. And for example, in sewage sludge and in freshwater purge, the most dominant congener is PBDE 209. But in open sea water and in marine fish, the most dominant is 47. But if you look on the purge from sea coast, the most dominant is again 209, which is followed by 47 and 154. Which in turn means that probably 209 comes to the sea coast with this biotransportation path. Why? Because 209 is big and heavy molecule, which is not really easily accumulating in fish tissues, and is not very well transferred through the food chain, and it is not very well atmospherically transported because it is easily degraded to other PBDEs. So this path looks quite interesting, and that's why the main conclusion here would be that Latvian sea coast is complicated and beautiful ecosystem. And it's complicated because, first of all, it has low salinity, and that's why, some fish species like perch are tolerant to live both in the sea coast and in the inland waters, as well as it is reached by lagoon-like lakes like Lake Liepājā, Lake Papes, and estuaries. And that's why a part of well-discussed and well-known transportation paths like atmospheric deposition, like runoff, also biotransportation is an important vector here, which should be considered in future. Thank you a lot.
Thank you so much. And I'd like to invite the next speaker, Sigurd Øksnevald from Norwegian Institute of Water Research. Again, the floor is yours.
We start with this one. Maybe. Well, my name is Sigurd Øksnevald. I work for the Norwegian Institute for Water Research. I'm a colleague of Sissel, but when we get this going, I will talk about risk assessment of contaminated sediments. Yay! Yes, so contaminated sediments can be toxic to the organisms living in the sediment. And if the the contaminants leak out from the sediments. It can also have effects on organisms living in the overlying water. And it can also have effects on humans and other predators if the contamination from the sediments enters the food chain. So, and you could say it has also a risk of spreading the contaminated sediment, the contamination from contaminated sediment area into the water and then to another cleaner area. So I will present some method or guidelines used in Norway, used to assess the risk of contaminated sediments. And this has been implemented by the Norwegian Environmental Agency, but this was developed by researchers from NIVA and also from NGI, the Norwegian Geotechnical Institute. And with this guideline document, there's also an Excel calculation tool for really calculation of this risk. So it contains a lot of formulas these threshold values for contamination in both sediments and water, and also threshold values for daily intake and weekly intake of seafood contaminated by the sediment, those contaminants. Yes. So the aim is to describe the risk posed by a contaminated sediment. So this concerns both risk to human health and the risk to the ecosystems and the risk of spreading of the contaminants. And this system is used as a tool to decide if remediation actions is necessary. So you can say there's a risk, a way of describing the impact of the contamination in the sediments, so that you can evaluate if there's an acceptable risk of those contaminants or an unacceptable risk. So as my colleague Sissel have already talked about this system, but yeah, so in sediment areas where the source of new contamination have been stopped, then we'll often have a goal of getting this class 1 or class 2 status, and also we have this demand of achieving good chemical status and good environmental status according to the EU Water Framework Directive. And this good chemical status, this could be achieved by doing, for instance, dredging and capping of an area with contaminated sediments. But then, in areas where there's still ongoing contamination, so some discharges from industry, then sometimes we set a goal of just getting this class 2 of moderate status, or if the ongoing contamination is quite high, then usually don't do any remediation there, so it's just postponed. Since, well, if you spend a lot of millions on dredging and capping contaminated sediment, and it's then getting a new dose of contaminants again, then this first remediation, you could say it's in vain. So, yeah. So here you see some of this 5-class system for metals, for heavy metals, and some of these PAHs, polycyclic aromatic hydrocarbons. But we also have these for a lot of other organic contaminants also. This is for this is a 5-class system for contaminants in marine sediments, but we also have the same system for freshwater sediments, and we also have the similar system for concentrations in marine, well, in seawater and also in freshwater. So these systems are based on information about toxicity from these contaminants, and for marine sediments, it's based on also toxic tests on various sediment living organisms. But then this will then imply that many organisms die in class 4 and class 5 sediments, and this is often the case. So we will see that there's not so high diversity of organisms in the sediments, in the most contaminated sediments. But then sometimes this does not make up the real picture at all, because if it's a high total concentration of one type of contaminant, it is not necessarily toxic. So if for instance, many of these polycyclic aromatic hydrocarbons, they are often very strongly bound to particles, and then they're not taken up in the gut of some sediment living organisms, and also many heavy metals are not bioavailable if they are bound to sulfur. So metallic sulfides are often not bioavailable and then not toxic. So the toxicity of these contaminants in sediment depends a lot of also other physical and chemical characteristics in that sediment. So in addition to measure sediment concentrations, it's also important to measure the content of total organic TOC, total organic carbon, and also type of sediments of the grain size. And it can be very useful to do some tests, just mortality tests of the sediment. So this risk assessment systems is in 3 levels, where the level 1 is quite simple, and then the complexity increases in level 2 and level 3. But then you take sediment samples, have them analyzed, and then might end up with having to do remediation actions. Yes, the risk assessment level 1, then you just take concentration of relevant contaminants in sediment and then compare it to some of these thresholds level of contaminants. So then, as I said, you need to analyze for relevant contaminants. So if you have information about what type of contaminants you have in the sediment, then you analyze for those contaminants. And if you don't know anything about the sediments in that area, then we normally analyze for heavy metals and PAHs and PCBs and also TBT. And we usually also do some toxicity tests. The Calux test, that's a test for well, dioxins or dioxin-like PCBs. But then again, it's still possible to do a risk assessment of sediments based only on concentration of sediments. So these toxicity tests might be quite expensive. So it's nice to have these also, but it's still possible to do risk assessment with only concentrations. So then we take sediment samples from the upper 10 centimeter of the seabed. And this is used because from experience, we have a standard method since most of the contaminants deeper than 10 centimeters usually don't leak into the overlying water. So we mean that the contaminants in the upper 10 centimeters of the centimeters are the one that will do the risk for both the sediment living organisms and the organisms in the water. And also there are, in the seabed, there's a lot of small organisms digging and causing some water currents when they dig holes and they eat of the sediments and then shit it out on the top of the seabed. So some of these organisms in the sediments, the top 10 centimeters, they have this bioturbation system, so they can actively cause some ventilation of water from the seabed and into the overlying water. So the most simple type of risk assessment, level 1, then we just compare contaminant sediment concentrations with threshold value from this 5-class system. So that's the threshold value for class 2. Then you get this factor of exceedance of this. So those red numbers are the factor, the sediment concentrations, the contaminant concentrations exceeds this threshold value. So here you see that especially PCB and a few of those pHs have too high concentrations for this type of risk assessment. And here's some of the heavy metals in the Kalusta channel, so some exceedances there too. And this system does not apply for oil in general, but for also pHs, which is often found in oil. But then for the risk assessment level 2, then we also assess risk regarding spreading of contaminants and also the risk to human health. So then the risk of spreading is calculated for risk via diffusion from the sediment to the overlying water, and also by this bioturbation caused by sediment-living organisms, and also from resuspension from ship traffic. So both big ships with the powerful engines and big propellers will cause some of those environmental contaminants to be resuspended from the top sediment and then into the water. And this will happen, well, all the time when the ship drive over this area. And there's also a risk of spreading via the food web. Risk to human health, this is calculated via local seafood, but also recreation from well, contact with the sediment, and or maybe theoretical if you swallow some of this sediment. Then for this level 2 risk assessment, we need more information to get a better risk assessment. Then we have to define this area that you want to assess. So we need the water depth, the seabed area, and the seabed area with a depth less than 20 meters. You need a grain size distribution of the sediment particles, and also this residence time of the water in that area. And you need some data for the ship traffic, so how many ship cross over this area. And you need some more chemical input also, and also these biological factors, so this toxicity test and also this whole sediment toxicity test. So the more information put in this Excel calculation sheet, then the better the risk assessment. So then you get some these red values for well, spreading of contaminants, then both by diffusion and active with organisms, and by ship propellers. Maybe not very exciting to see this, and then and this is some results from for maximum tolerable intake and a daily tolerable intake of contaminants in an area. And for this case, it was mercury that had too high concentration. And you get this in also this risk assessment level 2. And you also get the results for concentration in pore water, which then is the water that sediment-living organisms are mostly exposed to. Yeah, I'll skip this one to speed up a little. And this Excel sheet comes up with some of these figure, and this is the transport process for spreading of contaminants. It's by organism, ship, and diffusion. And this just shows that intake of seafood is the main risk to humans. And then to show that for risk assessment level 3, you get better risk assessment if you also have data for concentration of contaminants, for instance, in the water overlying the sediments, and also if you have a concentration in pore water in the sediment, or if you have a concentration of contaminants in the benthic fauna or in fish. Then you don't have to calculate concentration in fish to assess the risk to humans, but then you have actually measured the risk of eating the local seafood. Yay, thank you.
Thank you, Sigurd. You can already take the seat over here on the stage. Take the chair you like the most. Please, Marta, Sissel, and Natalia, please join us. We already have some questions from our online audience. I think it's a good sign. Marta, question to you from Inga Retiķe. What about microplastics transboundary pollution? Could it be that actually maybe the main source in some cases of microplastic pollution are our neighbors? And it's not our fault.
The short answer is yes. A few years ago we did a study. We mapped microplastics throughout two rivers, Liepājā and Daugava. The first point was near the border, and the following points were either upstream or downstream major cities. And part of the pollution comes in from the neighboring countries. Yes.
Okay, thank you. Another question from our online audience is to you, Cecil, from Anette Kupliņa. You don't have the chemical evaluation of TBT, right? Why is that? Is it because it's already banned and you assume that it will be not substantial, or what's the reason?
Yeah, the reason is that TBT is all over the Norwegian coast.
Oh, so it's the other.
That's
completely
the reason.
Different reason.
It's the completely different reason. And when we do measures, we usually don't consider the TBT because it's almost ubiquitous. It's all over, and TBT has been banned now. We also see that in biota. Because it can make that snails have different sexes, and we see that in the Karmsundet, one place that I presented. Now we see that the situation is getting normalized.
Mm-hmm.
So,
okay, the situation is changing. It is changing in the nature. You say that.
Yeah, like with the snails, these dog whelks.
Mm-hmm. And it is changing legislation-wise and business-wise too. The world is changing. What do you expect? Okay, of course, TBT pollution will go down eventually. It is already happening. What are other possible changes in coming years that you see, that which type of contamination could go down, or maybe there are some new polluting businesses which are coming in?
As you saw on the screen, we just had one measure with PFAS, the perfluorinated compounds, which is at European level now to be banned, and we see that the PFAS we found in rainwater, we found in groundwater, we find in biota, we find in sediments, we find it all over, and this is a substance that is used in millions of tons every year in our daily life, and I think this is the substance that will be focused on in the future now, and probably there will be a complete ban of use of these substances.
Okay, and are there any new chemicals coming in from new types of businesses, from new activities, or you don't see any?
We know that the EU Water Framework Directive is changing now because it changed every 6 years, so new priority substances will be included, and one group of substances that are not so, we have some pharmaceuticals, but pharmaceuticals will also be included more in this new round now, at least, yeah, in the EU Water Framework Directive.
Okay, thank you. Sigurd, about the assessment of contamination. I like the money questions. Are, let's say, businesses willing, or do they have to pay for assessments like that, if those are polluting businesses? Who is paying here for assessment?
Yeah, in Norway, many industry businesses who actually have high discharges of contaminants to lakes and coastal areas. They have to do monitoring and have to, well, pay for monitoring also. So, but in other places, the government or municipalities pay for this risk assessment. But some part of it can be quite expensive, so sometimes we choose not to do the most expensive parts of it, but still.
Mm-hmm. And when it happens that the government has to pay either for assessment or remediation, what's the general perception of the society? Is society willing to pay for that, or they assume that that's like, you know, green crazy hippies?
I'm not quite sure. There's some different cases, but for instance, in the Oslo fjord, some years ago, there was both the dredging and capping of contaminated sediment in the shallow areas along the harbor areas, and then there was a long debate and a lot of people protesting. They called it dumping of poison, because this contaminated sediment, they were, well, deposited it in a deeper area in the fjord, and then they covered this area afterwards with a 0.5 meter thick layer of both sand and thicker material, so it should be quite safe. But a lot of people protested against what they called the dumping of toxic material in the fjord. So.
Okay, thank you. Natalie, about the perch and mercury. As I understood, you did samples once per month?
Yes, but 2 years, as I remember correctly, 2019 and 20.
Are there any differences in mercury concentration based on season?
Actually, no. There's like one big trend which is followed mostly, and the only difference is that we expect that perch is more mobile during the spring. That's why maybe if we go so deep into the analysis, we could see some differences due to migration between the coastal water and the inland water. But if you just take the whole pool of the data, there are no like super huge outliers based on the months.
Mm-hmm. So why did you choose to take these samples every month? If
there's actually a good reason, because we are living in the north and our sampling season is quite short. Mm-hmm. Like it's not really easy to go and sample fish during the winter. So we have to do our best during the summer. This is first, and you never can to know in advance how much fish you will get. Sometimes we get a full net of fish, and sometimes we have just 3, and you have to do something with that. Like the latest sampling in September gave us three perch in Daugavgriva. So, and you have to be aware of that, and that's why it's very, let's say, a practical approach to do your best during the summer, and then to work with what you have. Mm-hmm. And to hope that you will find some extra trends there too.
Mm-hmm. And the concentrations you see in perch, would you say that it might have some impact on human health if they are eating the perch, or not really? We don't eat such amounts of
It is
perch.
The most frequent question I get. Yeah. There are like 2 thresholds. One threshold is for the environment quality, and another threshold is for human health, and one is regulated by the EQS, like environmental quality standard directive, another with regulation for food health, I guess, something. And they are very different. For environmental quality, the threshold for mercury is 200 micrograms per kilo of wet weight, and for food health, it is 500. So it is, if we just take this threshold and try to calculate how much fish we eat daily, it is not kind of unhealthy, not hazardous too much for human. But if we take this environmental quality standard, then it is exceeded all the time, and I don't think that we will be happy to know that, okay, we are safe, but there are no fish because everything died because there is super high pollution. And another point is, like, we are kind of lucky that we don't have such fish like tuna fish, for example, which take much higher trophic position than our perch. Our super predator is, like, in global scale, is not very important predator at all. So, but if we would have tuna fish, then it would be, of course, much worse than it is. Yeah.
Okay.
So everything is very relative.
Yes, I see. For human consumption, go ahead, but maybe human is not the most important thing in
exactly.
this.
And in our region, it's not global conclusion.
Okay, thanks. Yes, did you?
I'm sorry. Yeah, you wanted to make a comment.
Just a comment. In Norway, there are warnings about eating perch, I think, bigger than 100 grams, and also eating pike. Doesn't have to be a really big pike, and also eating big freshwater trout. There's also warning about this because of the high concentration of mercury in some freshwater fish, and so these warnings about giving food containing either pike or perch to children and to pregnant women.
Oh, well, I totally agree. I have to add, but it's hard to find here such big perch. If we take this, okay, we saw super big perch in Lake Liepājā, but they are very few. So of course, but these very few individuals, they really had high concentrations of mercury. It's true, and I also would not advise to eat it to children and pregnant women. But if we take like perch in general in Latvian waters, it's not so big.
Yeah, the only guidelines I have seen regarding health about fatty fishes like salmon is that you should, for pregnant women, you shouldn't eat it more often than once per week. But then again, in Latvia, no one really eats that often.
Exactly, it was my point. Like we are not eating fish three times per day. That's maybe if you would switch to this diet, I would then tell something different than I told before. Yeah, but yeah.
So here we have to focus on this as an environmental, not a health issue.
Health also, we have to consider it and keep it in mind that yes, fish is contaminated, yes, mercury is our problem, yes, like river and lake fish is more polluted, but like we are kind of, at least legally, we're kind of safe, yeah.
Okay, legally safe.
Legally safe.
Sounds good. Marta, I noticed that in the graphs, and you also mentioned that usually the concentration of microplastics in waters were higher in summer. Why is that? Because you mentioned that it's not related to tourism, microplastics. So what's the reason?
The connection to tourism was related to plastics in beaches, microplastics on beaches, but in water, in surface water of rivers, and also in lakes, so we observed it was higher in summer. I'm afraid to say why, because it's only we tested it only for 1 year. We took one sample in each season. It might change if we do it also next year and the following year to see some trends. But from this one observation that we did, it was higher in summer. It might be related to the amount of water there is. Maybe there was some heavy rainfall that flushed microplastics from land to rivers. But to say sure that more microplastics is always in summer, we have to do more measurements.
Okay, so in this case, it could have been a coincidence that there was a meteorological...
Could be, but we saw it in every river that more microplastics were in summer. But to say sure that it is like that, we have to take more measurements.
Okay, so we have to talk about this maybe in 10 years again.
Yeah.
And then you can give some conclusions. In this experiment you did together with this swimsuit producer, with washing swimsuits and checking what's going on with microplastics. You mentioned that it would be a good idea for producers to wash their clothes before they are selling it. Could you suggest how they should do that so they don't produce a lot of microfiber pollution?
So what we learned in the experiment was that microplastics retaining bag can be a solution to catch these, to put a textile in those microplastics retaining bag, wash them, and then you catch yourself the microplastic fibers. And another option is that it's possible to buy like filters to put to connect to your washing machine that filter out the microplastics before they enter the sewage system.
Mm-hmm. And actually I see one more problem this could solve. We know that in fast fashion there are a lot of production which is like really low quality and which is destroyed after the first wash. And if the first wash is at the producer's side, they can't sell it then afterwards. So that would be a bit more safe for a customer to buy something that is possible to wash.
Yeah.
Are there any questions here in the audience?
So I have a question for Sissel, Niva. In your presentation, you mentioned expressive amount of financing what was spent in Norway for remediation activities. And the question is it in Norway, is there some specific government or municipality programs or financial instruments that can be available for private owners who have problem with polluted places? And what is the instruments for the stimulation to remediate it, or for the private persons or for the industry? Thank you.
Sometimes, like if you buy a property and the sediment is contaminated underground, and then you have to clean the site, but sometimes you don't have the money, and if you are not, this is an old polluter, sometimes it can even be the state, like the military, that has polluted the site, or other municipality activities. And then there's this kind of sharing of the cost, actually. So in the national budget, we have every year a certain activity on remediation of contaminated sediments and soil. And people can apply for these every year, this funding. And usually if there's like the place that I showed her today with the expanded polystyrene used for build construction material, and where they previously used brominated flame retardants. And this is an industry that is going very, very well, and they have to pay everything for remediation of the sediments. And so it's a mixture, I think.
Yes, and for the groundwater part, for example, where it's not so easy because it can be involved a lot of polluters there. And in Netherlands, for example, there are state government funding for solving the groundwater problems. And how is the experience in Norway?
In Norway, we don't use much groundwater.
Yeah, because
we mainly use surface water for drinking water.
Okay.
And yeah, groundwater is not a
not the topic.
Issue in Norway, but of course you are not allowed to pollute the groundwater. Like we see that with some of the PFAS substances, they are very mobile and they don't degrade in the environment. And some places we have problems with it. This, especially at airports where they have been using fire-floating foam, and then the groundwater is polluted. And then in some places, the owner of the, well, in Norway, the owner of the airports are the state, and they have to provide people with drinking water that are not contaminated. But cleaning of the groundwater in Norway, it's not, and there's not much activity around that, actually. Sorry.
Maybe it would be interesting to go and actually evaluate what is the quality of groundwater.
Yeah, we also have the groundwater directive, which is a daughter directive of the EU Water Framework Directive, and we also do measurement in groundwater. So you
have some idea, although you are not using it very actively.
We are obliged to do monitoring, and we also have monitoring of groundwater in Norway. So, but we don't use it much.
Okay.
No.
Any questions from the audience? Sigurd, I would like to ask you more about risk assessments. You are assessing different chemicals and their risks. Are you assessing also the mixtures of, I don't know, different heavy metals or PCBs or anything? What happens and what's the risks? What are the risks when they come together? Or there are too many combinations to even start?
I think there are many combinations, but in this risk assessment tool, this Excel tool, then we get some numbers of risk for many contaminants. But there are some other people at NIVA from the ecotox section that have been working on testing of this cocktail effect of several contaminants, but we don't have this cocktail effect as incorporated in this kind of risk assessment. So no, I think there are many combinations to look upon and to consider in that case.
Okay, thank you. Cecil, one more question to you. What did I want to ask?
Can I add something to Sigurd?
Yes,
okay.
Because I just remember what I wanted to ask, but please go on.
Okay, or to anyone here. And there's changes in the EU Water Framework Directive, and today we also have this, you look at one concentration and evaluate the EQSs, but according to the news from the Norwegian Environmental Agency, that there will be changes in this in the EU Water Framework Directive. You will look at more substances together for evaluating a risk. So this is probably coming in the already next year or in 6 years again, because it's evaluated every 6 years, these substances.
You were evaluating a list of substances, many of them. And of course, I guess in any sampling point, you were assuming that taking into account that there is this and that industry, most likely there will be this and that pollution. Did you have any surprises that you took the sample and you see a concentration of something which doesn't make sense? Were there any mysteries?
Maybe the one in the Sandefjord, this area where we have this painting industry, that they are exporting a lot of painting to other countries, and we found very high concentration in the fjord, and we have to go back and look at the data on the report, and it appeared that we first thought it was something wrong because the concentration was so high. But it appeared that this has been a dump site from old time, how they did it earlier, and so that was maybe one of the surprises. I don't know, Sigurd, you were also part of the project. Were there any surprises?
Maybe not that project, but I could say there's also another group of these chemicals called siloxanes used in various makeup and skin creams and so on, and they also have some bad effects, and the producers know about them, and and they accumulate in fish and end up in the fjord systems. But then the funny thing or the strange thing is that there are some concentration limitations for this product that contains siloxanes that are being like washed off when you take a shower or so, to kind of protect the environment. But then those concentration limitations are not the same for those products that you really put on your skin. So that I would think there are, well, effects on those using those products, since those concentration limitations does not apply for those that just go into your skin and then so surprising and quite bad, I think.
Okay. Thank you for the story. Anyone?
Yes, we have two more questions.
Yes, about the plastics. I don't know if you know, if you have an opinion, but about those new biodegradable plastics, do you think they will bring relief to the situation?
There are two kinds of bioplastics or biodegradable plastics, the ones that are made from renewable resources, but they are still synthetic polymers. They just use natural monomers to create synthetic polymers. And the second one is that they create bioplastics that degrade in certain environment. We have seen already a lot of plastic bags, plastic cups that are marked as biodegradable, but the problem is that they are biodegradable industrially. They need a certain temperature, certain humidity. They will not degrade just in the environment. Like, for example, in Latvia, where there's winter and minus 10 degrees in summer or autumn, it's maybe too wet to degrade. Not completely.
Scary as well. I have the question as well for you, Marta. Is there some estimations about the microplastic source types in the Baltic Seas? Example, exactly for the Latvian region, and as well, is there emerging conditions from the EU to make some restrictions to use the microbeads example for the cosmetic and so on? Is this coming as well?
About the sources, it's globally quite the same. Usually they come from human actions, from house, the same wastewater, from cosmetics that just flush down the drain, from washing textile and washing machines, tire wear from traffic. Now it's common to make those sport fields or kinder playgrounds, child playgrounds with soft rubber, this sagums. Yeah, like
sources.
Yes, surfs. And also the fake grass on football fields. Those are the places where over time plastic degrades and it gets flushed into the environment. Also, in cities it's common to see that there are these big garbage containers that are opened, and either wind or birds take out the trash.
And how is with the fishery industry?
Sorry?
Fishery industry, how is with this source?
Yeah, that also a lot of industrial fishing. They lose those trawls, nets that still after their initial purpose they go around the sea, the ocean, and they catch those live animals that get entangled in them. and over time also they break down into microplastics.
And legislation, how is with that? Is it coming up in the EU?
It gets more and more common to include microplastics in different aspects in this legislation. They, as you mentioned, they forbid to add intentionally add microplastics in products. Now there will be in the Water Framework Directive to monitor. It's suggested to monitor the microplastics also in freshwater, in lakes and rivers. And there is already a request to monitor microplastics in marine environment.
Thank you.
Thank you. There is one last question from Rita Poikane to Sigurd. Your assessment system, is it published somewhere?
Yeah, it's open published, so you can find this this guideline and also this calculation tool on the Norwegian Environment Agency's website, so it's possible to download those. The guideline is in English also, and this calculation tool is, well, there's one in only in Norwegian, and there's one where it's not completely translated into English, so I don't think it's perfect for non-Norwegians.
Yes, but yes. It's available, yes. And if a person has an ability to translate a bit, it's available. So for our online viewers, wherever you are watching this, either on Facebook or YouTube, we will add the link to the publication next to this recording, so you can access this assessment system published. Okay, now it's the time for so-called real discussion or coffee break. I'll be waiting for all of you back here 20 to 4 or 15, 40. Thank you so much for your presentation and presentations and the discussion. Let's go to the coffee break. It's just here as before. And stay with us.
You and your colleagues.
What?
We had extra.
Thank you. Thank you all for being so patient and disciplined as well. I see that most of you have returned to our venue. And we have approached our last part, and this last part will be divided in two parts. Today we have talked about pollution concentrations, about how to manage and store data, about risk assessments and so on. And what is left now is, of course, remediation, because we want to deal with this pollution in the end. Now we will have 2 presentations, then coffee break, 2 more presentations, then a panel discussion, and then we are done. So the first speaker is Inta Dimante-Deimantovice, and she will speak about what do we know about alum water treatment for phosphorus removal in lakes, and what's alum is. Yes, Inta is here. Please, floor is yours.
Hello. I must say I have never felt so confused before my speech, because just some 10 minutes ago you were listening how aluminium can be a toxic substance and can be like really bad to be found in sediments. And now I'm going to tell you what good we can do by adding aluminium sediments. So, you know, there are always different stories behind different subjects. So I'm going to tell about a new project what we just recently started, what is called Trust Alum, in order to build trust in alum concept in general. So what does it mean, and why it's important to talk about it already now at the very beginning of the project, before we really start any treatment and restoration of lakes. So hopefully I'm doing fine. No, that's not the one. Help? The grade. Yes, thank you. So this is our project acronym and also a full title, so you can find it easily on the internet and follow our activities. We are trying really to post a lot and tell what are our upcoming events and what we have done so far and why it is important. So, in short, this project is to help public authorities in the Baltic countries make better use of alum water treatment and improve water quality in lakes. So far, so good. Sounds brilliant. And our project team, really, it's a dream team, because we have, we brought together different authorities, municipality, where lake is located, also environmental ministry, because those authorities are the ones who can actually in future support such activities a lot by providing supportive funding. And also we have as our partners also State Environmental Service in Latvia, what are authorities actually giving technical regulations, issuing permits to do such activities, and also controlling how it's happening. So, project in a nutshell, what's a problem when we talk about alum and why it should be used at all? So, our project is tackling one of the greatest challenges in the Baltic Sea region, what is eutrophication. So, eutrophication is a load of nutrients, and in lakes, this key nutrient often it's exactly phosphorus. So, what is happening because of a lot of phosphorus, we get algae blooms. There are so many algae that zooplankton is not able to consume it all. So those algae are sinking down, and in this process of rotting using a lot of oxygen. And so there is a decrease of oxygen at the bottom of the lake. And because of this limit of oxygen, also phosphorus goes back in a cycle. So this is continually goes like a never-ending magical cycle. So phosphorus is released from sediments, and again, due to that, there is increased growth of algae, and that's how it is circulating again and again. So we are talking about something what is so-called external loading of phosphorus, and this is something what we would like to cut this magical circle and to stop. So in a way, we would like to immobilize phosphorus. So those are consequences of algae blooms. This is how it looks like, and this picture is exactly from that lake that we are going to treat. So that's a typical algae bloom picture, what you can observe during hot summertime. The project is introducing alum concept in lake treatment for the first time in the Baltic states. So neither in Latvia nor Lithuania or Estonia, and we have also been a project partners from all Baltic countries, alum concept treatment has never been done so far. And of course the question is why, and why we should start doing it. Alum concept in basics, we talk about aluminium salts that are used to form permanent bond with phosphorus in sediments. Easily, like explaining, it means alum is making a bond with phosphorus, and this phosphorus stays in sediments and is not going back in a circle and not becoming a part of food for algae. And yeah, so there are two most common substances used in this treatment. One is really called alum, what we took our project name from, and another one is PAC. And in both cases, the principle how it works is the same. So when added to water or sediments, it is forming another substance, what is keeping phosphorus in sediments. So it looks like this. Once you add this substance, phosphorus stays in sediments and is not included anymore in this water nutrients cycle. We are transferring knowledge from Sweden, where this approach has been used for nearly 60 years already. So we are collaborating with our Swedish colleagues, and in Sweden this method is really popular. The first experience goes back from 1968, when a lake called Långsjön was treated for the first time, and another treatment for the same lake was repeated again in 2006. So by seeing those numbers, you can already evaluate how efficient this treatment is and how long effect is lasting. But it depends on several factors, and I will tell about them a bit later. So there are hundreds of documented treatments in Sweden. And it's not only lake where alum concept is used for treatment. Actually, it is well known both for drinking water treatment, cleaning, and also for wastewater cleaning. And recently, I have been also visiting the largest wastewater treatment plant in Latvia, what is called Daugavgriva, and I asked, why don't you use alum here? And they said, well, we use iron, and it's just a matter of price. So method was well known for them, but sometimes you also have to consider your budget, available funding when choosing among methods. But the main story what I would like to tell from this slide is that it's not only for lakes, it's actually already known from other mattresses to be treated and to be cleaned. And you can treat both water and sediments. We choose that we go for sediments because we consider it to be like more to the point, straightforward, because we are trying to immobilize so-called historical, due to different anthropogenic activities, loaded phosphorus in lake sediments. And so this project, however, is not so much about treatment than building trust. And why? It's because of those facts. Despite facts that aluminium forms about 8% of the Earth's crust and is the third most abundant element, still there are a lot of bad associations concerning this chemical element. Yes, it can be toxic at certain concentration, and it also depends on a compoundment how it is present. And according to European Food Safety Authority, since aluminium is very common on Earth, of course it also gets into our food, water, and so average European population representative is exposed to aluminium. So it is, you see those numbers, 28.6 to 214 micrograms per kilogram of body weight per day. So it's something that we are actually, in a way, intaking anyway every day because of environment. But what is maybe a good news is that aluminium, what we are exposed to, it's like goes through our body. It is not bioaccumulating, and we can see it clearly by, like for instance, if there would be analysis done and like blood, bones, feces, urine would be checked, and definitely some traces of aluminium will be found. That's a fact that we have to consider, because I mean it's a common element on Earth and it will be always there. And it is really in this. I mean, this is kind of a first project where this society involvement is so important, because when we had our first social event, talking with local people, we got a lot of stories and a lot of there were a lot of worried people who were thinking that, okay, now water will become toxic and I will not be able to swim there anymore, and there will be no fish and so on, because aluminium is something very bad, because we know already from the past that it's not good to use those old vintage type of cookware made of aluminium. Like people already know that using such kind of things in a kitchen, especially when you are cooking acid food like tomatoes or things like that, there is a leaking occurring, and this is how we also intake aluminium. Same time, I think it's not a surprise that still we are using aluminium foil in a kitchen. It's a very common thing to be find in shops, and somehow people rarely are connecting those two things, that one, what we are considering good, is maybe not so good considering aluminium in other type of form. What else, as an example, when talking with people and society and explaining the role of aluminium and how it can be found, because basically people understand aluminium as this silver light metal. But for instance, there was a big concern about perspirants and deodorants used in body care. And there were a lot of titles declaring that don't use usual ones because they contain aluminium and it can be bad for your health and it can be bad for your body. So instead, those crystal deodorants were advertised to be safe and nature-friendly. But actually, if you look at the content of those crystal deodorants very carefully, you see that it's a mineral salt, and to be more precise, it's alum. It's aluminium salt, the same, but can be used also for lake water and wastewater treatment. And moreover, since we are already at the second half of the day and a little bit tired, so don't really forget every time if you give a present ruby or sapphire, it's also aluminium oxide in this case. So aluminium can be found and be present in very different forms. In very different compounds and substances. Still, if it's whether it's really a magic tool and super method that can be everywhere and we can treat like every lake and get rid of eutrophication, what is one of the greatest concerns in the Baltic Sea region. Not really. Because there are some things that have to be very seriously to be kept in mind before considering alum concept treatment, either it is alum or PAC in general. So the first one is if you have high external phosphorus loading, then actually binding phosphorus from internal loading will not really help, because you will get extra more and more, and this effect of treatment will last maybe just a couple of years. So it's very important to consider what are phosphorus loadings, both external and internal. Low pH, it's just what we discussed during a coffee break with Norwegian colleagues, that low pH is a limiting factor for alum concept involvement. You cannot treat lake neither with alum or PAC if you have a low pH already in a lake. Very shallow lakes, that's also not possible because of technical things. So you need to have a lake at least 2 meters depth. And you have to have them in certain pH range. So this is why, for the moment, before alum treatment, we are carefully inspecting and monitoring a lake every week to understand what are changes of pH at different depth, what are concentrations of different elements, oxygen. We are also collecting a lot of different environmental abiotic and biotic samples, investigating phytoplankton, zooplankton, doing scientific fishing, and so on. More practical things, maybe a bit trivial, but still, what else to consider? You have to check like what are load capacity of surrounding roads, and you will see a bit later why, because the whole technique for treatment is really heavy one. You have to consider also if there are some maybe archaeological objects, cables, pipes, everything what is related with bottom, with sediments, what can be destroyed. And then there are 3 very important things. You have to consider what kind of protected species are living in a lake. A depth map has to be built. That's mandatory. And the most important is there is a geomathematical model that has to be built before, based on data collected, to calculate how much actually aluminium substance has to be added. And if we talk about bad examples, if they are present in the past, of course they are. I mean, there is no method that could be developed without success and fails. And in this case, those bad examples are exactly from time when those models were not used and people were more like, using substance, maybe not that exact concentration. So the consequences were that either there was no effect or pH dropped and effect was like a bad impact on ecosystem. It can be restored, but it takes some time. So it's really important to build this model before treatment, and maybe also during building model you will understand that actually maybe this method is not the best one to be used. My own personal belief is that this method is more for really eutrophied urban water bodies, what other way could not be recovered. So this is how it looks like from a company in Sweden called Wasservatten Research, who is really doing this treatment. And they are showing, this is their example, they are showing how treatment takes place. So you see form of a lake, and you see there it's based on model, it's described how many, what is the dose of aluminium substance added to sediment. So it doesn't really mean that it will be the same in every place of lake. It can be very variable depending on phosphorus in sediments, how rich sediments are with phosphorus. And how long it's gonna last, is it really efficient? Is effect forever? There is a paper written by authors of different institutions, and the first author is our collaborator, Brian Husser, who has been doing a lot of treatments and calculations of these geomathematical models. And his main conclusions were that out of data based on 114 lakes in Europe and North America, they calculated that, but you see this range is actually between 0 and 45 years. So we also consider examples from past when model was not used. So on average, we talk about 11 years for lakes, when you really can see this effect. And there are some factors to what impact success of aluminium treatment. It's of course dose, how much you've been adding, whether it's a right one or maybe not that really. Is it cheap or shallow lake? And Is external loading continuing? That's what we talked before, that you really have to make sure that the external loading is reduced significantly. And also, bottom-feeding fish have a negative impact because they are, disturbing sediments. And just very short about the lake, what actually will be treated in Latvia. It's going to happen next year in April or May. It's a lake called Valnezers. It is located in an area of capital city. It's a small lake with the deepest part around 5-6 meters. And there has been a lot of anthropogenic pressure throughout the years on this lake. It is a suitable place for this treatment because apart from evaporation and precipitation, there is like almost no other water exchange, so we are quite sure that we are really dealing with internal loading of phosphorus. Historically, there have been a lot of uses of this lake, like it has been used for laundry washing, livestock watering holes, surrounding land used for agriculture purposes. Also, horses were taken there to drink and to swim, and horses are not only drinking and swimming. And so in general, this is nowadays very heavily urbanized and used for recreation place because there are building blocks around these lakes and around this lake, and of course it means a lot. How the treatment will happen? There is a specially adapted and built boat, and it's a patented method. You can see some parameters describing, that's why I mentioned that you really need to have a stable roads, or those roads actually sometimes are specially built to get this technique to the lake. It will be, like Lego, made in parts in Sweden, placed in containers and taken to Latvia and then built together again. So self-treatment will take maybe 2 days, but all the preparation will be quite a time. What do we expect? So there is an example from Vaxjö Kommune in Sweden. So you can see how lake looked like with a blooming algae before and how it looks like after treatment. And what we also expect, we expect situation with phosphorus. I'm sorry, it's in Sweden, but in principle you can understand. So there is a phosphorus amount showed, total phosphorus. And you can see that after alum treatment, those green bars are showing how amount of phosphorus found dropped. So this is something what we also would like to expect after a treatment. That's it. Thank you for your attention. Looking forward to your questions.
Thank you, Inta, for advocating on aluminium as the good one. Exactly, it's your turn, Martin. Martin Romanchuk from University of Helsinki on in situ treatment of oil spills everywhere.
Yeah. It's nice to be here. I have been many times to Latvia, but never to this place. So it's interesting to see tomorrow what we are going to be presented. I will quickly, I have a lot of slides, and I will quickly go through different methods that we have developed for mainly for in situ bioremediation by biostimulation in most cases, but in some cases also chemical and other methods. In situ, I talk about in situ, which means that it's underground without digging anything up. And then there is ex situ, which is either on site next to the place or off site, that it's excavated and dumped somewhere and supposedly treated elsewhere, but you never know. So, but we have been mostly working with this part. But one issue is this monitored natural attenuation, which is a good euphemism in a way for doing nothing. But you have to monitor, and you have to be sure that something goes in the correct direction, that it does clean itself. But if it doesn't, which we will go through, you have to do something active. And for example, in situ, instead of excavation, is the only alternative if you don't want to tear down the buildings on top of it or under roads. And there are many techniques nowadays, but authorities, for example, and contractors and builders, etc., they are suspicious because it's not so fast and it might fail. So in most cases, still in Finland, and I guess in most places, excavation is still the most common method. But natural attenuation, to do nothing, you can choose, for example, all the sites in Finland and then rank them according to which ones can be left to be treated by themselves, that they are naturally remediated. And then you can concentrate on treating those where you have some benefit from it. So, but the bottlenecks are that the temperature is low underground, even in the summer. If you go deep enough, it's low. And then there is a lack of electron acceptors like oxygen, but also many others can be used. And then if it's organic like oil, then nitrogen and phosphorus is normally low or too low for active kind of biological remediation. So here is a picture that we have now in a new review that we wrote, and it's coming out, I guess, next week or something, that depending on the contaminant that goes either in the surface soil, or it might go through the surface soil, especially if it's permeable soil, and to the groundwater, and if it's light, non-aqueous phase liquid like diesel oil, it starts to float on the groundwater, and if it's dense like PAH, etc., it goes into crevices in the bedrock. So depending on the situation, you have to choose a method. And these are, I won't go through that because I have instead examples of these. First example is a fuel station that had very high concentrations of diesel and gasoline and also lubrication oil. But it was not very big volume, but it did threaten the groundwater. So if there is no threat of spreading and it slowly gets better, then you can use natural attenuation. But if there is a threat to the groundwater, then you need to do something. And they, the authorities had concluded that here we have to do something. And we were involved together with a company that in many cases have gotten these cases. And we used electrokinetics. Electromigration is that charged particles move according to polarity, and electroosmosis, which is the more interesting part in a way, is that in dense soil you can push in or through water with nutrients, solutes like nutrients and bacteria. We have shown that as well. And then if the soil is not dense, then the electroosmosis doesn't work, but the electromigration still does work, and temperature does rise. But there is then a moisture gradient formed because the water goes towards the cathode if the soil is dense. So it will be dry here and wet here. But then if it's a natural situation in a field site, there might be new water coming from here. This is everything above the groundwater level. But also there are other problems. pH gradients are formed. pH goes down here and up here. And here, on the other hand, is oxygen released, and here is hydrogen gas released. So oxygen here is a good thing for the microbial degradation. This is just a clumsy picture of that situation. We had a gas station that they did not want to remove. So that's why we got this opportunity to test. And we had infiltration of nutrient-rich water from the top and from the anodes. and the water went that way. And it did degrade the diesel in about half a year. But there was some gasoline left in the soil. Gasoline monoaromatics are more difficult to degrade than diesel oil. And also the parts that were dense soil were still a problem here. And we used also Fenton reaction, in other words, adding hydrogen peroxide at 10 to 12%, which will kill all the bacteria. So after the bioremediation, we added hydrogen peroxide, and it cleaned everything that was coarse sand, because everywhere else it didn't go. It didn't go into the dense soil. But then we left it with the electricity on and didn't add any water, and it dried this area. So the gasoline could actually, after this treatment, be removed by soil vapor extraction, which was not possible in the beginning because then it was too wet. Then nothing happened with soil vapor extraction here, but when we had dried it, it worked fine. And that's kind of what we did here. And one point here, I won't go through this, but one point is that in each case when we ran into problems, we did tests in the lab and found a new solution. And then the contractor realized that solution in the field, and it worked. So that's one, and here is the big scale. This is our transformer, a big transformer that can give up to 40 amperes. Not very high volts, only 270, but very high wattage because of the amperes. And this is the line of anodes, and the water goes this way. The anodes are not visible here. And this is then the next experiment. This was a real accident in Iisalmi in kind of middle Finland. And we got the opportunity to test our methods for this type of situation. This was not now dense soil, but sand soil. So we did it in our soil research station, Soilia, which has 16 of these 2 cubic meter lysimeters. This is from above. And here we did it to mimic the Iisalmi situation. Here we even put humus soil on top of what the students do. And this is the result, that natural attenuation worked somewhat, but very slowly, and there was leaching of diesel oil towards the groundwater. Biostimulation worked fine, and everything that was released from the soil was degraded, but pretty much was still present in the soil after this half-year treatment. But kind of the environment was protected. And then we tested also Fenton, but it worked only at the surface, and then the peroxide was used up, but the rest was biologically treated then, so it's in a way it still worked. Here we are having this accident with this is the truck that turns over, and this is a mixture of diesel and gasoline, because the truck had both of those. It worked, and biostimulation protected the groundwater. That was the big issue here. Then the next, this was an old industrial site near Lahti, and there had been an accident 10 years earlier, and it still was spreading towards the groundwater. So here we used the same method. I don't need to explain it so much, but we introduced nitrogen, phosphorus, and oxygenated water here. And this is again how they did it, and it worked. This is the starting situation up to 3,000 milligrams per kilo, and after only 11 months it was gone. 100 milligrams per kilo was acceptable. But then we did it the same in Sweden, in Motala, and there the problem was that the challenge was that it was under the groundwater level, and it was still fuel oil. So how did it go there under the groundwater level? Apparently, because it's next to Vättern, the water was going down, up and down, and once it moved down and attached to the soil particles, it wasn't released by the water coming up. So here we tested the same method, but it didn't work because in cases where the contamination is above the groundwater level, you can heat up the soil. I didn't mention that before, but it went up to 28 degrees, for example, and that's ideal for microbes to degrade oil. But in this case, the new water was coming all the time from the left in this picture, so it didn't heat up more than 1 degree, so it didn't help. But some oil was still released from here and was floating on the groundwater, so it was kind of going towards the Vättern. So in practice it did clean, but not the way we wanted, not by biostimulation. Here is, we added in trenches nitrogen, urea, I think it was here. This is then one family house that had an oil tank that was leaking oil for many years. This is the area that we treated. Here we used this Fenton reaction. In other words, like I mentioned, fairly high concentration of hydrogen peroxide, and it was easy to add here because we just added it into the oil tank and made bigger holes so that it was kind of seeped into the soil. And after one treatment, it was 72% down. Second, it was actually not helping anymore. So then we started biostimulation and in this case we brought in new bacteria. We had kind of disinfected the soil with that peroxide. So in this case we used bio-augmentation. In other words, that you add microbes. And it worked. It was not as fast. This was in 2 weeks. 1 week, second week. This was 2.5 months, 4 months, and 16 months. And we did get it down by over 90%, and that was considered acceptable. So it was kind of approved by the authorities. So, and then we found another use of using hydrogen peroxide, namely peroxide sparging. This is our invention in a way, that you can have air sparging by pushing air into the groundwater and it bubbles. And for example, MTBE is volatile, so it will come up from there. But we used instead peroxide, which will kind of spread more in the groundwater and then start bubbling, and then you can get rid of what is volatile there. And also the peroxide will degrade, oxidize contaminants. So I will, in this situation, the MTBE was released very rapidly, but when we had also soil, it was much slower. And this is without the soil, it was in 1 day gone. And with soil, it was kind of rebounding. It went down and then it came back up, probably because it came down from the surface again. But it was still, this is a logarithmic scale, so it's 100 times less still here, so it was a success. And here you see why. I mean, this is diesel that goes to the surface and stays there, and if it's volatile, it goes up in the air, and partly by the peroxide it will be degraded. So, and this is a case in the field that we used, and it starts bubbling on the surface. And then another totally different case again, that we pumped up groundwater added nutrients and oxygen and circulated the water. And also the contaminated water that spreads, it starts flowing in the opposite direction, and it can be kind of downstream regions can be salvaged that way or saved. And here you can see that with the treatment it went down very rapidly. And then we had nanoremediation with zero-valent iron, and there if you have oxygen, you will create reactive oxygen species, and that will degrade the contaminants. But if you don't have oxygen there, the nanoiron will create reductive conditions, and that's good for the anaerobic bacteria that can do the dechlorination of compounds. And this is just a picture how you can use it as a wall or as a plume above some heavy fractions. So I won't go through this because I have some also about water. This is cotton grass, which is a byproduct of peat excavation. And of course, peat, they try to stop using that, so that might be a problem for this case. But it is very good. If you have diesel oil, mussels die. But if you have cotton grass added, they don't die, but they have some tissue damage in our experiments. And for example, here, after 7 days, if you add cotton grass fiber, they will, the oil goes down and the mussels survive. If you add the cotton grass and leave it there, even though the oil is still there, the mussels also survive. And the oil is kind of, actually it was the other way. This is with, you leave it there, this is when you take it away. And this is when you do nothing and everything dies, and this is the control. So if you bind the oil, it will not hurt the mussels, for example. And then we did try to create, grow microbes for bioaugmentation, and it did work. And we tested if a natural beach contains degrading bacteria, and they do. I mean, this is natural sand, artificial sand. In natural sand, the oil concentration goes down faster, so that's the main thing there. And this is then a project that we had together with Russian groups and Estonian groups, and the red ones are contaminated, the green ones are clean. And we compared the microbial composition. And this is, Jaak True has done this with his group, and found that in all cases there are microbes with degradation active genes. I mean, they contain genes that are active in degrading aromatics and oil, etc. We didn't here, at least yet, see much difference between clean and contaminated sites, but this is ongoing, so we might have a change there. This is just, I won't go through this, but this is the of this review that we have published, that if you have a contaminated site, natural attenuation is one option, but biostimulation is the one that we try to promote, and only as a last resort, excavation. So thank you.
Thank you so much. And we are slowly approaching the last part of the last part, but before that we will have a quick coffee break. Please be back at 20 to 5. Just a short break to freshen up, and then we continue with 2 presentations and a discussion. Thank you. I must admit that you're a wonderful crowd, very disciplined, right on time. So 2 more presentations, then a discussion, which had already started during the coffee break, obviously. And then the day is done. Let me invite Vallo Kirgma from Estonia to talk about monitoring and reducing chemical pollution.
Okay, good evening. My main work is in Estonian Environmental Research Center, and over there I'm doing the similar IP project as Linda is doing here in Latvia. We have quite much in common in that regard. But if I have to compare these 2 projects, then Linda is focusing mainly on the natural conservation areas or something like that, and we are on the northeast part of Estonia, where is very much of industry, very much of mining, and due to that also we have quite a lot of residual pollution. And during this project we are actually cleaning some of them. We have been we remediated with exit method already Kohtla-Nõmme factory. Erra River just was finished, so I can't speak about that very much. And in Pahnimäe asphalt concrete factory, this kind of approach was this time done that before going to the field, and they are trying to find the best way for in situ treatment over there. They made several lab tests like that ministry made a contract with one of the environmental companies, and that environmental company contacted each different kind of in situ providers, and then they tested them to see which one is the best for that kind of conditions. But about that I can't also talk about today. It's very difficult today for me because I have to talk about the monitoring results, but I don't have any, as we are doing the monitoring at the moment. But just to get the picture, what we're dealing in Estonia is that the same as in Latvia and Lithuania, we had a lot of different historical pollution in Estonia, and we have basically inside the country we have divided them into the 2 categories, and this division was done so that pollution that happened before 1998 is defined as a residual pollution, because we don't actually don't know always who's the responsible, except for that it was made during the Soviet Union time, and they are connected to some kind of accidents or not so much accidents, etc., etc. And also these sites we have divided into the 2 categories as well, that are in areas of national importance and areas of local importance. And these ones that are of national importance, they are usually very big areas or very difficult areas. So the government has been trying to find solutions for these areas, and they have been, let's say, quite successful till this time. But all the so-called newer pollution is based on the polluter pays principle. So if you pollute something, you have to clean it up as well. Most of these so-called residual pollution sites, they are mainly from industrial or military areas, so it means that they're also, we are mainly talking about oil pollution and other components connected to that. but we have had like very different areas, like for pesticides, etc., etc. And just to get the picture, there was one of the previous talk was about Norway, how you do make the risk assessment. For us, it's a little bit more easier or difficult, I don't know. We have one of regulations in Estonia for soil that says if you have like, there are sorry, how can I go back? There are 3 different categories. So it means if the number is the smallest, we consider the soil to be clean. And the middle one means that this is a quality standard for residential area, and the biggest number means basically it's quality standard for industrial area. And it seems to be at least working on some level, because most of the contaminated sites are threatening the groundwater, and after the contamination has been removed in one way or other, we have been seeing some little increase in the quality of the groundwater. But as the IP project is an integrated project, I will be focusing today on the Purtse catchment area. This is the area which is actually by 2 different different oil shale industries, and the Purtse River is actually between of them. These industries are mining, but also producing oil shale oil. And in Kohtla-Järve area, the oil shale oil is also used in local scale for some of the other chemical industries that are producing, for example, these phenols that are needed in the, what the women put into the face. But we have quite a lot of issues with that, because there were several accidents during the Soviet Union time, and both rivers, Kohtla and Erra, that are tributary rivers to River Purtse, they were contaminated, and the sediments were, you can say, they more look like as an oil, not as a sediment as such today. And we have, and for example, for the Erra River, there has been also stories from the 1960s that the river was burning in one point. Today, we have to evaluate these rivers by the Water Framework Directive and assess their status. And it's sometimes it's very difficult, because for sediments and the sediments are polluted at the moment. For the sediments, there are no quality standards, at least in the EU level. There are some in our national level, and I've been looking for the other numbers as well, what we have been seeing today, just to compare where we are at the moment. And it's very difficult to assess sometimes the impact of this pollution, because for the chemical side, we know that the chemical status is bad, the sediments are contaminated, and there are high levels of oils, pHs, heavy metals, phenols, and these are coming from the industrial area. I can't show. Or did they come? But if I look at the ecological status, then it's already very, very difficult to understand if they have any impact on the life in the river. Because, for example, the benthic interbates, they are also very sensitive about the hydromorphological changes in the river. And this river has been changed already. It used to be It used to start from the south region, but all this part is today is already dry, and the main river comes from the former mining site. So we can say it's a natural man-made spring that is full of sulfides, is full of different metals, and the reactions are still going on, so we don't know what will be coming there in a couple of years. We know that today we have nickel, today we have some other metals, but we're expecting that it might change in a while and something else is coming. So when they had to make the environmental impact, so to understand how much or what is the connection between the biota and the pollution, then scientists from the Tartu University finally managed to prove that the salmon in the Purtse River had different signs of sickness. They were alive and they were there, but they were not doing very well. Meanwhile, if I look at the environmental ecological status in the Kohtla River, for example, the fish are poor not because they are poisoned. They are poor because they can't migrate. There is a dam in the Purtse River, and the migrating fish can't come to the Kohtla River. And this is the reason why this indicator is bad. So within this project, just before the ex situ works started, we managed to take samples from both Erra River, Kohtla River, and Purtse River, and tested different chemicals from water, sediments, and also all the indicators for ecological assessment. And in addition, for the sediments, we collected in Kohtla River, for example, in 3 locations, the sediment samples to test the toxicity, to see what's happening there, and to see if after the remediation works, is something going to better or not. Just to understand the area, I can't, sorry for the guys in there. This is the Kohtla River that we have here. And as you can see from the so-called red dots from, no, this one is working, yeah. Okay. Before the excavation works, all the pollution was mapped, and so all these points are from the sampling. We took almost 2,500 samples over there just to understand where is the pollution, how much is it, and how much it has to be removed. And this is Kohtla River, this is Erra River, and this over here is Purtse that goes to the sea. As you can see, Kohtla River was all polluted from the beginning to the end. And this part of the river actually is not the original one. This is the outflow from the former mine, and it also contains all the mining after mining processes are going on. So this one is full of surprises still till today. The wastewater, the industrial area is over here. There's one of the biggest mountains in Baltic states, I believe. This is a semi-coke landfill. And around this area we have also phenolics wetland, we call it, because this, when the landfill was built, everything that was dangerous was put in there in one point, just to get rid of it. And as to that, we have so-called phenolic wetland over here. It's actually was growing for some time, and it came by ditches to the river also. And in this area, it was also so wet that they couldn't remove the material, so the bypass was built over there. Most of the remediation works looked like that first they had to bypass the river, so the temporary ditch was digged, then the soil was excavated and it was supposed to be treated in the same location, but when the work started, they couldn't get that kind of factory from Finland, so it went actually back to the Kohtla-Järve landfill. So it's on the landfill again. And after the treatment works were finished, the river was also put back into the place, and last year they finished it while putting also some hydromorphological elements over there just to increase the variability and add some habitats over there. So they put some rocks and some spawning spaces, etc., etc. Within the, phenolic wetland, this is by this big mountain, this is the landfill, and it looks like that. It used to look like that. There was actually no good solution at that moment when they started doing it, so they are collecting the water that is contaminated highly with phenols to the leachate ditch that is surrounding this landfill, and this leachate from this is also pumped to the basins, and from the basins to the wastewater treatment plant, and there it is purified as much as is possible. But within the wastewater treatment plant, we also could see that in one point they started having troubles. They couldn't get the wastewater treatment processes all running together. So we had to do some inhibition tests over there as well. And we could see that if the load from the hydraulic load from the leachate is exceeding 6% of the total load of the wastewater treatment plant, then the nitrification basically they lose. So this is like always balancing the loads. And if it happens that they don't pump it to the wastewater treatment plant, then these ditches are not working, and it also starts to, again, to escape and goes back to the river. So we are like balancing on the system. Unfortunately, I can't talk about monitoring results today. I can only compare some of these numbers because I don't have all the numbers today. Even today we are taking the samples right now. But for the sediments, I can show you that we managed to get rid of the phenols. We managed to decrease the contents of PAHs, contents of oils, contents of metals, with, of course, some exceptions because the nickel and lead are coming still from the mining site. And it should look good. It should look very well. But this is like the bad news. We are still, I don't have all the toxicity tests at the moment. I'm still missing one. But already I can tell you that in some points the situation is, from the side of the toxicity, is even a little bit worse than it used to be. This unhappy phase means that some of the test organisms were damaged. This one means basically that one of the tests was failing more than 50%, and this one means that one of the tests failed 100%. So we have acute toxicity over there at the moment. Will it be better? I can tell you in 4 years. Then we have finished with that. So messages for Mordor. Thank you.
Thank you very much. And the last speech will be about Liepājas Karosta Canal that you are going to visit tomorrow. And now we will hear a story about it, so you can see tomorrow. Ivo, the floor is yours.
Thank you, and good afternoon to everyone. Actually, as this conference actually was opened by the speech of the general manager of the Liepājas Special Economic Zone, so we have came to the logical end of the sessions, so to the presentation regarding the Karosta Channel remediation project. My name is Ivo Koliņš, I'm project manager. Actually, I'm working with this project already for 24 years. Actually, I came to Liepāja to work for the Special Economic Zone in 1999, actually, and this was my first project, actually. And then, yes, that was quite an interesting time, so that, let's go. So, that's more for the foreign people, actually. The Liepāja is the city located on the eastern coast of the Baltic Sea. It's quite strategically located, and therefore, actually, we have all these issues with the old military pollution and other things. So, few facts. So, the Karosta Canal was built, excavated. The excavation started in 1890. So, and the Soviet Army used this territory as the naval base for the time period of approximately 50 years. So, when Russian Federation, at that time it was already Russian Federation's Navy, left the Liepāja port in 1994, actually approximately 700,000 cubic meters of polluted material was left at the bottom of the Karosta Channel. So, and as contamination was made by the Soviet Union, actually polluter pay principle cannot be applied. So, that's the case for us. So, here we can see some short summary of the project. As already said, I started in 1999, but the first activities regarding the pollution of the Karosta Channel actually started already in 1992, when the Soviet troops actually didn't leave the Karosta Channel. So, at that time, it was determined that, or found actually that. One part of the Liepāja port is heavily polluted, and that's the Karosta Channel. Fortunately, the other parts, actually, as a free harbor, winter harbor, commercial channel, and others, actually was cleaned. So, and first activities started in 1996, when there was a number of international missions, actually, which participated in the first phase of the Karosta cleanup project. Actually, one of the main was the Danish environmental engineering company COVI. So they were very, very involved in this process. And as a consequence of their activity in 2001, actually, we built the disposal place. Actually, we enclosed 7 hectares of the most eastern part of the Karosta Channel by building a sheet pile wall. The length of the sheet pile wall is 256 meters and the width is 8 meters. As that's also my project, actually, I know that by heart still. So, and what's the good news that actually we enclosed the most polluted part of the Karosta Channel. Approximately 11% of that 700,000 cubic meters actually was already enclosed at that deposition place. So, at 2004 actually started the second phase of the project. We started the very close communication with the Ministry of Environment and Regional Development, actually, and as a result, it was attraction of the financing of the European Union Cohesion Fund, and in 2015, actually, we implemented 2 projects. The first one was a pilot project for approximately 10 hectares of the most polluted part of the Karosta Channel, where we excavated approximately 60,000 cubic meters of the polluted materials. And the second project was regarding the excavation of the technogenic pollution of the Karosta Channel. Ropes, not submarines, but airplanes, old passenger cars, and whatever you can imagine. So, and starting from the 2018, actually, we are working on the third phase, and actually the logical end of the third phase is the Karosta Channel remediation project, which is supported by the Norwegian financial instrument. So, and initially we planned that 164,000 cubic meters of polluted materials will be removed, but as a matter of fact, actually, in the middle of the summer, actually, we had unforeseen problems with unexploded ammunition, and we were forced actually to make extraordinary UXO risk assessment, and as a consequence was that we cut off 11% of the total territory where actually this excavation works cannot be performed. And therefore now we are talking about the 145,000 cubic meters of polluted materials which will be excavated as a result of this project. So, and there is also the fourth phase, because we are not removing all the material. Actually, we are removing approximately 40% of all the polluted material, actually, which is still located at the bottom of the Karosta Channel. So, and therefore, we are working on the possible scenarios, actually, in the very close cooperation with the NIVA, Norwegian Water Institute, and this morning, actually, I received very good news that as we have the savings within the project due to the fact that we are going to decrease the amount of the polluted material to be excavated, so we have the saving in the project, and we have got the conceptual approval of the Ministry of Environment that we are going to the more value-added cooperation with the NIVA. So, and we are looking forward to transfer the knowledge regarding the risk assessment. Actually, that was the issue which was presented by Sigurd today. So, and the final closing of the project actually and the disposal place is planned by the year 2035. That's a short resume. So we have the several goals. Actually, the long-term objective is to reduce the negative impact of historically contaminated sediments of the Karosta Channel on the environment, human health, and the ecological status of the Baltic Sea. Our short-term objective is to remove. It was planned 164,000 cubic meters. Now we are talking about 145,000 cubic meters of non-compliant sediments containing 298 tons of the hazardous chemicals. And of course, there's the monitoring. Actually, the monitoring was started in 1992, as already said so, and we are continuing with annual monitoring of the clean material disposal site in open sea and monitoring related to the Nature 2000 requirements like Liepājā. So, starting from, I don't remember, but starting from 2015, as I believe, actually, we started regular groundwater monitoring. Actually, that monitoring is more oriented to the disposal place, as 60,000 cubic meters of polluted materials was deposited at that place. So, and therefore, we made the 6 boreholes, which are regularly analyzed or observed. So, and there you can see actually all the parameters actually we are doing. So, and there will be the few tables actually. This will be quite light presentation without any scientific value added, but but few tables actually will be present. So this table shows the concentration of the heavy metals in groundwater. So you can see actually we have five monitoring sessions starting from the 2015 when the disposal works actually was completed, and up to the 2020. So as you can see, for none of the elements actually there are no red lights, so meaning so that we are not below the limits. That's a good news. So there we can see concentrations of pollutants in the groundwater. Actually, so it's monochromatic hydrocarbons and concentration of pollutants. Actually, as you can see, actually for few elements there are some concerns, but as we see, so starting from the 2020, actually we are talking about the target value or little, or the values little about the target values. So we also are performing the surface water monitoring. So you can see that we are monitoring all products and six heavy metals. So which are most common for the pollution of the Karaoste Channel. So we have the 9 monitoring points within the area of 78 hectares. So, and there we can see the summary of our monitoring in 2012 to 20, as well as 2016 and 2018. So, as we can see, actually, so the situation is the following. So in 2016 and 2018, actually, there was a few places with the elements with the concentration within the sea level. So, and that's also quite interesting issue, because when the Karaoste Channel was observed first in the 1992, actually, one of the conclusions was that there is no macrobenthos species in the Karaoste Channel at all. It was completely dead. So now we are talking already about the more or less normal macrobenthic situation within the Karaoste Channel, and so meaning that the environment of Karaoste Channel is going to be healed, I would say so. And as by the end of the 2023, the final removal of the pollution from the Karaoste Canal's bottom has to be carried out, the impact of the remaining concentration of the ecological situation in the Karaoste Canal has to be defined. So in order to do so, actually, before the excavation work started, actually, we made sampling of the Karaoste Channel water area for the macrobenthic species, and we'll do the same when the remediation works will be completed at the end of this year. So, actually, if we are talking about the monitoring sites, we have the 3. The first one is the Karaoste Channel. As I already said, we have the regular monitoring starting from the 2015. Actually, the site number 2 actually is the soil disposal place. Actually, when all the soil material which are excavated from the Liepājā port, except of Karaoste Channel, and is being deposited at the open sea soil depository. And the third one is the commercial channel, where the selective monitoring has been carried out. So, and here we can see, actually, as I already said, if in 1992, actually, there was no macrobenthic organisms in the Karaoste Channel, now, actually, before the excavation work started, actually, we are talking about such a situation. So here you can see actually quantity specimens and also the biomass. So that's a quite interesting information, because as I already said, in 1992, actually whole port territory was monitored. And in commercial channel, sorry, no, it's, I went so far, too far, sorry. Actually, in port we have the two channels. So how can I get the red point? Oh, it's the red line. Okay, we have the two channels. Two artificially made channels. One is the Karosti channel, actually, and the second is a commercial channel. In the case of commercial channel, of course, it's connected with the Liepājā lake. So, and if in Karosti channel, actually, there is no life, at the 1992, actually, it was completely dead. In commercial channel, actually, the macrobenthic organisms was found. So, and here we can see actually the situation the commercial channel had in the 1992. Frankly, actually, also the commercial channel was not exploited in very good manner, as the Soviet troops actually was located there, as well as the auction fishery fleet. So, and here we can see the number of macrobenthos organisms in the data groups at the total biomass of Liepājā port sediment disposal site. Actually, that's a site number 2, actually, where the all soil sediments which has been excavated in the port of Liepājā actually is deposited at the open sea. So as you see, also at the open sea depository, actually there is quite a good macrobenthic situation. So, and here actually we tried to find some correlations in between the concentration of the heavy metals and oil products with the organisms and biomass in the Karosti channel. Actually, as you see, of course, for the certain issues there could be some correlations, but if we are talking generally, actually the correlation didn't find. We didn't find any correlation. And there we can see the situation before the remediation project, which is carried out this year, was started. So we can see that that there's some areas actually where this concentration of the heavy metals and the oil products actually is most serious. So, and actually a few hours ago, I had the possibility to get famous because the local television actually shoot the video with me, actually, and the first question which was asked by the reporter actually was, can I say that project is completed? No, project is not completed, because we are still continuing with the excavation works. For the moment, actually, approximately 80,000 cubic meters is excavated. Altogether, we have the 6 remediation work sections. 3 sections are completed, and 3 sections should be completed within the next coming months. And excavation works are made by two excavation units. Actually, one is the backhoe copper dredger, actually, which is very good to excavate material on the slopes, and when this thickness of the layer actually is more than 1 meter. The average thickness of the layer of the polluted materials is approximately 40 to 50 centimeters, but it varies from the 20 up to the 1.5 meters. So, for the transportation to the sheet pile wall, actually we are using the hopper barge. And sorry, there was not, I have not a picture with also the trailer suction dredger, because for the parts where this thickness of the polluted material is not so big. Actually, I would say up to the 30 or 40 centimeters. Actually, the suction dredger is used as the most appropriate equipment. So, I'm going forward. And a few words about our disposal site. Actually, as I already said, in 2001, actually, we enclosed 7 hectares of the most polluted part of the Karvoste Channel by the dividing sheet pile wall. And yes, it's quite unique technique for the Baltic Sea, because I know only one project which is similar to this. That's in Finland. Actually, it's a Vuosaari port. Actually, where the new Vuosaari port container terminal was built. Actually, the territory of the site is quite similar. It's approximately 7 or 8 hectares. Actually, the depth also is quite similar, approximately 10 meters. That site was filled with polluted material. In Helsinki case, it was mainly TBT due to the shipbuilding activities. And at that disposal place, all this polluted material was stabilized by the cement, and the ground for the new container terminal was created. So, and now there is this nice small container terminal is being operated at that previously polluted site. But technique is not new, actually. It's more utilized in the Netherlands, in the Benelux countries. So, and the biggest one actually is with a capacity of 90 million cubic meters. So that site is made by the Rotterdam Port Authority and will be used for, I don't know, next coming 20 or 30 years. So, and it's mainly used for the polluted excavated materials from the Maas, Scheldt, and all other rivers, actually, which has the impact on the Rotterdam port activity. So, and yes, therefore we're also thinking what to do with the deposition place while the project will be completed. Actually, we have two options. The first option is to leave it open, as it Netherlands examples, or actually we can go to the way of the Helsinki port and close and stabilize this deposition place, actually, and we'll get additional 10 hectares for the further port development. So, thank you very much.
Thank you for the presentation. Yes, take the best seat. And I'd like to invite Inta, Martin and Valo to come here as well. We have some time for our last discussion. Our online viewer Elmira Boikova was adding that in Karvoste Canal you had already some research done by Latvian Institute of Aquatic Ecology and Institute of Biology in the 90s. So the work has started very, very long time ago, and I think this case shows that maybe it's better not to pollute if it takes 40 years of active work to clean it up afterwards. Also, Elmira had a question to Inta, but I think it's actually a question to everyone about the affordability of all these remediation techniques. She asked how much does it cost in Sweden to remediate this lake by adding alum. Probably you don't know the exact number, how much did it cost, but generally, is it a costly method or not?
It of course depends on a size of lake, how large lake you would like to treat. But I would say that in our case it's quite expensive, but it's also expensive because of this heavy logistics we have to plan. I mean, we don't have a boat here. We have to, as I said, you like take it down in pieces and you bring it here and then you build it up again. And also, we are really extra carefully doing all kind of analysis and monitoring at different ecosystem levels before. Usually in Sweden, they don't do it in such details, but we do it to be sure ourselves and also to convince society, because our goal is to build trust in this method. According to information from Sweden, prices can be very different, and usually those are municipalities who are paying for such kind of treatment, because for municipalities it's more easier to ensure funding needed, because they also get in Sweden partly support from a government. But those, in any case, those amounts are like something around starting from 15,000 euros. But as I said, those are very rough estimations and really depends on a size of lake.
Okay, thank you. Martin, the methods you mentioned, in situ methods of remediation of oil products everywhere. Again, the question why it is not used everywhere, is money the issue there?
Well, partly it's money, but partly it's that excavation happens immediately and then you know that it's done. And in this case, this in situ remediation takes longer, but it can go on under the ground without disturbing the surface. So that's what we try to promote. But the costs, in most cases here that I presented, it has been cost efficient, about 30% on average cheaper than excavating and bringing new pristine soil. But for example, in the Motala case in Sweden, under the groundwater level, and the case that I was asked during coffee break, that in sediments, the consumption of electricity would be quite high. So that would make it more expensive. But in above groundwater level, when it's semi-dry or moist or something like that, kind of meadow soil, then it is really cost efficient. And it is, in most cases, always, also fast enough, but you always have to know what you're doing. So, I mean, a contractor that says that, yeah, we can do it, they might not know what they are doing. So you need expertise and to know when to say that something else is better. So that's a key issue.
Mm-hmm. And I guess another problem might be that in a case of excavation, general public can easily see that the bad stuff is taken away, it's not there, fantastic. But in this case, well, you tell me that you did there somewhere, I can't see it. Is it actually changing? Or I mean that for general public, it's hard to see the effect. It's hard to believe that something's actually going on.
Yeah. Well, I mean, in general, the general public trusts those who take samples and official sources and environmental institute, etc., that they do report the real situation. So in most cases, it's not a problem.
Okay, so you actually have the trust in science, in society.
Yeah, and
Good
also when you excavate, you take it away and take it somewhere. And in many cases, it is treated there, but not always. It used to be that it was just dumped. But nowadays, it's treated there somewhere else, which also increases the costs. And then you have to bring from somewhere new soil. And also the logistics about that is pretty polluting and expensive.
Mm-hmm. Okay. Valo, you mentioned one of the cases where you actually had to move the river to a ditch temporarily, and then you do the excavation works, and then you move the river back. Sounds crazy expensive, was it?
I was just trying to calculate how much was it. I think it's about 1.2 million per kilometer, or something like that. But I know that we have been knowing it since the very beginning. We will have difficulties because North Estonia is sitting on the limestone, and limestone is like a highway for every kind of contamination. So it basically hides in there, it can move from there, and it quite easily can come up again from there. For example, not today I focused on Kohtla River, but Terra River. The last part that we, in the LIFE project, were cleaning, this was in the karstic area, so the contamination is already inside the limestone, and it can surface and can go down again. So we are like hoping for some kind of middle way that quite a lot of has been excavated, but we have to look for the natural bioremediation, or if that's not enough, then we have to start a new project and do something else again. I'm hoping we don't have to, but it might happen.
Okay, thank you. And Ivo, 40 years of project. That's almost like Rolling Stones. You know?
That's not really. For me, it's only 24.
Yes, but the end will be 2035, and the beginning was 96, so more or less 40 years. Simple question, was also money the issue not to make it in 10 or 20 years?
Actually, yes, I would say the money is the main and only issue for this project. Because now we are excavating these polluted materials on the parts of the channel which is more utilized by the ship movements, and due to turbidity, actually there could be some emission from the sediments, so that we are solving most urgent issue actually, which is related to the activities at port. But coming back, I don't know, to the beginning of 2000s, actually, we also had several issues, or the several options, actually, what we can do. Actually, we also had the suggestions, or to make the capping, for example. But if you are talking about the Karosh channel, is the active part of the port, actually, we cannot do the capping because the depth of the channel will be decreased by a meter or even 1.5 meters. So that there was quite a many options, actually, which were studied, and we stayed on that disposal place, actually, as a more appropriate. But we have some rough estimates that in order to complete this project ex situ, actually, actually, how to say, actually, if we would remove all the polluted material from the Karosti channel bottom and would deposit at the deposition place, it will cost approximately 50 to 70 million euros. And that's very costly. Therefore, now we are looking to the in situ part site, actually, and those approximately 200,000 cubic meters, which is still located there. Actually, we will try to we will try to do the remediation in situ. Thanks.
Okay, thank you. Are there any questions here in the audience?
I will have.
Man ir tāds neliels jautājums, Ivo. Jūs stāstījāt, ka ir 4 fāzes šim projektam, un katrā fāzē ir piesaistīts finansējums. Man interesē, vai, teiksim, kāda ir Liepājas speciālās ekonomiskās zonas rocība, vai ir šī, teiksim, arī šī institūcija ir pašpietiekama un arī kaut ko pat par savu finansējumu var veikt.
Let me translate. This lady said that in your presentation there were a story about the project. It has 4 phases and with finance. So does Liepājā economic zone, special economic zone, has enough finance on its own, and how is it applying for money and where? So where the money comes from?
Yes, show me the money, yes. Actually, that's quite a tricky question because we are talking about the truly or a 100% environmental project. Actually, as a Liepājas Special Economic Zone Authority, we are not earning anything from implementation of this project. Therefore, if we are looking, for example, to the standard development projects, actually, then of course we have some incremental cash flow and other things. So, and that's a proof for the credit institutions actually that the project can be financed. In this case, of course, there is no reverse cash flow, and therefore, of course, we are looking to the third-party public financing, as already was mentioned. The polluter pay principle cannot be applied. So, and of course, the Liepāja Special Economic Zone Authority also are investing our own financial means, or the monitoring program, actually, for example, or all the preparation for the attraction of the financing from the public institutions. Actually, all those activities are financed by our own budget. And that's not cheap.
Okay, thank you. Any more questions from the audience right now?
I have a question for Martins for this in situ technologies for the peroxide usage. Actually, is there some restriction in Finland, for example, for gas, what is coming out like result of the reaction when you are using this type of remediations?
You have to take it into account, but I'm not. I don't think there are strict rules about that. But it has been this company Nordic Envicon that has applied for permission. So, for example, MTBE that we kind of evaporated, it's not considered a problem because it's the concentrations once it comes out from the soil are very small anyway.
Any more comments, questions here?
I have, if nobody else is, no? Okay, I have a question for Martin. Can you tell, isn't this bioremediation process used the native microorganism cultures, or these are some miracle efficient organisms from abroad?
There are those miracle preparations that you can buy, but our experience is that bio-augmentation to add microbes is usually not needed. But you can do it just in case to make sure if you want to. But that's normally just extra expense because biostimulation is what you need. And if you have an old site that is kind of has been there for many years, there are for sure microbes there that can degrade. You just have to improve the conditions so that they can do it faster, like oxygen, heat, a kind of proper temperature, and these nutrients that they need. But in one case where we killed all the bacteria, then we also added new bacteria.
So basically, it's like supporting natural ecosystem services of the earth. Interesting, thank you.
Yeah, you just manipulate the conditions to suit the local indigenous population.
Thank you.
Sorry, it's quite unusual, but I also have a question to Martin. Actually, as I already said, we are going to remove the polluted material from the territory of approximately 30 hectares. What would you suggest, actually, if there are some possibilities to fasten some recovery of the benthic at that territory where all this material will be removed?
Well, without knowing more, it's difficult to say. And also, did you say benthic kind of animals? I don't have very much experience about those, but I do have colleagues that could give you advice about that.
No, that was just a fast question because actually that is one of the issues we'll be working in the next coming, I think, few months.
Yeah, but probably if I got all the data, I could make an evaluation. Can I help or can I not? But maybe I could.
Okay, thank you.
Comes one more question.
Again, for the Martins. In Finland, when you choose remediation technology, is it ex situ or in situ, you need before to have environmental impact assessment where you are comparing two different alternatives, same for the costs and for the impact to the environment?
You have to have a permission to do something that, I mean, some kind of ecological and risk evaluation, that you don't cause problems. But you don't, I don't think you need to, the comparison of different methods is more like that you compare different contractors who proposes what, and then you can choose from there. But all those solutions have to be approved by environmental or local environmental authorities, that you have permission to do those things.
Yes, and I would like to comment that in Liepājā case, it took years for each phase to receive these permissions, actually. And not so much money problems, that we spent about 10 years for each phase to receive all permissions from different institutions, that our conception is good, that it can be realized in real life. And in Latvia, this is the very bureaucratical way. And however, for the works, we have only, for example, 1 year or 2, what is crazy. Actually, we prefer to have 5 years. Maybe it's better for us, safer, but impossible normally. And especially for the large scale of the project, which is the Liepājā case, it's not a small project. It's actually the biggest military project in the Baltic Sea, actually. I don't know the bigger project in the water field. That's okay. We should fight with bureaucracy.
Yeah. Yeah, I know that this is a problem in Finland as well, but it varies between different regions. So it seems to be dependent partly on who makes the decision locally. And some authorities don't want to take responsibility for anything, so they say no, just in case, kind of, which is silly.
Vallo, would you say that bureaucracy in remediation projects is a big problem in Estonia, or you don't really see that as something important?
As from the part of bureaucracy, in our case, the ministry is doing quite a lot of big projects, so they are dumping it a little. But no, I don't see the issue. When there was a little bit before, there was one discussion about how, if you have to compare different technologies, etc., etc. We have like most of the cases, we have to already prepare the the basic project when you have to already compare as opportunities, and then you can go for all the way as you have to go.
I have a question about comparison between different techniques to INTA. You said that in the wastewater treatment plant, they said they are using not alum but iron for treating it, so because it's cheaper. So what's wrong with iron? Why not to use that in lakes?
The answer is very simple, because of oxygen.
Okay.
You need to have oxygen to do this treatment with iron efficient. And in our case, this lake already starting from approximately 2.5 meters depth to the bottom, it's almost zero oxygen. So it's not suitable also, for example, not for fish to live there. And so treatment with iron cannot be done.
Mm-hmm. And you also mentioned that there could be some problems if you use alum in a water body with protected species, protected fish species. What kind of problems are we talking about, and what species are we talking about?
I was more thinking about not direct problems, but that you have to consider it with extra like to be extra cautious about what you are doing. I know that in Sweden they use this method also for specially protected areas, and it goes fine, but I think it's important to understand for what reason this area is protected. I mean, whether those are plant species, are those species that are maybe connected with sediments, because of course sediment layer upper 10 centimeters are impacted. Because you could see this boat, it consists of like tubes that are to inject this liquid, and then after it's visible in sediment layers, it's like marks of this treatment. So, I mean, all those kind of things need to be evaluated by experts who can give advices and decide whether this method is safe enough for protected species.
Okay, thank you. Any more questions, comments, objections? No, not anymore. I can totally understand you. It has been a long day. Thank you for your presentations. Thank you for the discussion. Most of you will meet tomorrow when you will have a trip to Karosta Canal, and you'll see with your own eyes everything Ivo was telling you about. Let's meet here 10 o'clock tomorrow morning. At the first, we'll have a little presentation and a little film, and afterwards you'll be going to Karosta Canal to see it with your own eyes. The venue is open from 9:30, so don't stay outside in the rain. If it's raining, you are welcome to come here. I bet some of you will have even more fruitful discussions tonight wherever you stay. And I bet that tomorrow as well, when you stand by the Karosta Canal, you'll have a lot of questions, comments, and maybe objections.
Sorry, and one small remark from my side, actually, as I will be your guide for the Karosta Canal remediation site. Actually, we will have the bus visit, but with the 2 stops, actually. There is quite a bad weather prognosis for tomorrow, so that actually will be windy and rainy, so please dress warm and from rain protection, protected. Thank you.
So if you have a fancy dress with you, and if you have a raincoat with you, choose raincoat tomorrow. Yes. Thank you for being here. It was great hosting you.